Hi everyone. Can you please confirm if I'm audible? Okay. I think I'm audible, right? Okay. So let's get started. So now we are going to see many questions in minimum spanning tree and what are the algorithms for the minimum spanning tree and what are the theorems for the minimum spanning tree, right? Okay. So let's get started. Okay. So let me start with with the definition of minimum spanning tree, and then we will see some theorems, and then we will see many questions which are in the gate also and in our test series also. Okay. Okay. Now I think there is no echo and everything is fine. So what is a spanning tree? So before I go to the minimum spanning tree, can you tell me what is a spanning tree itself? So a spanning tree, so suppose this graph is given to you, then there are many spanning trees. So what are the spanning trees? A spanning tree is basically an undirected graph that is connected a subgraph which contains all the vertices, which has no cycle. So which means if this is a graph, then whatever tree that you have that which contains all the vertices, which means if this is the graph that you have, then whatever tree which contains all the vertices and no cycle. So all of these contains all the vertices and there is no cycle. That's why this is a spanning tree, this is also a spanning tree, this is also a spanning tree, this is also a spanning tree, right? So these all are spanning trees. Now what is the minimum spanning tree? It is the cheapest way to connect the graph, which means for example, if this is a graph that is given to us, then there are many spanning trees are possible. For example, these are the three spanning trees possible, and out of these three, this middle one is the cheapest way, right? Because this is having weight 71, so this is a minimum spanning tree. So the middle one is minimum spanning tree, and all of them are spanning tree. All of them are just a spanning tree, but the middle one is the minimum spanning tree. Why? Because the weight is minimum. Okay, I hope everyone knows this. Okay. Now, what is the minimum spanning tree of this given graph? Can you tell me? See, if this is a cycle, then let's suppose these are the 1, 2, 3, 4, 5, 6, 7, 8 edges, right? These are the 8 edges. Since these are the 8 edges, then can you tell me that how many edges will be there in the minimum spanning tree? Edges in minimum spanning tree? How many edges will be there in minimum spanning tree? Then answer will be 7, right? Because if these are the 8 edges in the cycle, then minimum spanning tree or any spanning tree will be having 7 edges. So if these are the 7 edges, right? If these are the 7 edges that you are going to have, then can you tell me that which edge you want to remove? See, you need to remove one of the edge. So obviously you will be removing the most heaviest edge, right? So this is the minimum spanning tree of this graph. See, this graph is given to you, and if someone asks you what is the minimum spanning tree, then you can, if this is a cycle, then you can just remove the highest edge, okay, highest weighted edge. So that's why this is a minimum spanning tree of this graph. Okay. Now, now, what is a brute force way to find minimum spanning tree? So, what you can do, let's suppose this is a graph that you have, right? Let's suppose like these are the many vertices, these are the many vertices, so, and so on, right? Suppose this is the graph that you have. Okay. So, suppose something like this. Suppose this is the graph you have. Then what you can do, you can list out all the spanning trees, list out all the spanning trees, and find minimum. But this is not a feasible way, but this is not a good way. Why that is the case? Why this is not a good way? Because let's suppose for example these are the n vertices, and this is one, and I mean total, let's suppose these are the n plus 2 vertices, or maybe these are the n vertices, let's assume, right? Then I think for every vertex there are two choices. I mean you can connect by this line or maybe by this line. So approximately I'm telling you there are 2 power n, right? 2 power n spanning trees are possible. Why? Why 2 power n spanning trees? Because let's suppose these are the n vertices, and each of them, okay, and this is one more vertex, this is one more vertex, each of them is having two choices. Basically either you take by this edge or you take by this edge, right? Something like this, right? Approximately I'm telling you there are 2 power n spanning trees are possible. So if there are 2 power n spanning trees are possible, then can you list down all the spanning trees and find the minimum? Do you think that 2 power n spanning trees If these are spanning trees possible, let's suppose, for example, right, if these spanning trees are possible, then do you think you can list down all of them and find minimum? List down and find minimum. Do you think so? The answer is big no, right? Because this is exponential. Since this is exponential, so we cannot do the brute force manner, right? So this exponential takes too much time actually. See, for example, if even for 2 power n, if n equal to, let's suppose, 30, then this 2 power 30 is so big number. This is a huge number. Okay, this is a huge number. Let me just tell you that this number is so huge that even if you take the lifetime, okay, to compute the minimum spanning tree of a graph, then you won't be able to do it. Okay, it will take lifetime to list down all spanning trees and finding the minimum. Okay, so it is a huge number. Just for n equal to 30, it is a huge number. Suppose n is 100, it is a very huge number, right? It is a very huge number. So that's why it is not possible. Okay, now there are basically two algorithms, right? I mean, brute force way is not possible. Hence we have two algorithms which are, you might be knowing it, which are Kruskal's and Prim's algorithm, right? Prim's algorithm. So we will see these algorithms and we will see many questions based on these algorithms, right? Okay, we will see many questions based on these algorithms and we will see these two algorithms. Let's just see. So there are two very nice properties of MSTs. So before I tell you these two algorithms, okay, so before I tell you these two algorithms, let me introduce you to very nice properties of the MSTs. First property is called cut property. Another property is called cycle property. Let me just tell you that what are these properties, right? Cycle property and cut property. So there are two properties that we are going to see first, and then we will see the algorithms. Okay. So let me just tell you what is the cycle property. It says, okay, I'm assuming all edge weights are distinct. Edge weights are distinct. Okay, so what does the cycle property says? It says that it is a very nice property. It says that, let's suppose you have a cycle in a graph. Okay, you have a cycle in a graph, right? So let's suppose this is a cycle. I mean, there could be many other vertices, many other things happening. Okay, but let's suppose this is one of the cycle that we have. So here I'm just listing down one of the cycle that we have in a graph. Now let's suppose these are the edge weights. This is 1, this is, let's suppose, 5, this is 3, this is, let's suppose, 10, this is 2, this is, let's suppose, 4, this is, let's suppose, 6. Okay, these are the edge weights. Then what does the cycle property says? It says that whatever is the heaviest edge, okay, heaviest edge in the cycle will never be part of MST. So this is the heaviest edge in the cycle will never be part of MST. Okay, this is the heaviest edge. So what do I mean by that? Suppose if I give you just this graph, okay, we have already seen this kind of graph. Suppose if I give you this graph and I ask you that what is the minimum spanning tree of this graph, then what you will say? You will say that, okay, if I want to find the minimum spanning tree of this graph, then probably this is having the cycle, then I will not be having obviously the heaviest edge. Why will I be having the heaviest edge? Is this clear to everyone? That there is no point in having the heaviest edge here, right? So if I want to find out the minimum spanning tree of this graph, then I will not be having this heaviest edge here. Okay. So the cycle property says the almost same thing. It says that, let's suppose that let me just prove this. Okay, let me just proof of cycle property. Let me just prove this. Suppose that this is the MST that you have. Okay, and this is the cycle. So basically, let's suppose that whatever the tree, this is the MST I'm writing. Okay, so basically the MST means there is no cycle and so on, right? This is the MST that you have. Now let's suppose there's a cycle. I mean, there's a cycle, and we have chosen some other edge instead of choosing the basically instead of neglecting this heaviest edge, we have taken this heaviest edge. Let's suppose we have taken this. Okay, this is the heaviest edge which is having the weight 10. Okay, so this is the heaviest edge. Suppose we have taken this heaviest edge. So which means what? That there is some other edge which is connecting. Since this is a cycle, there is some other edge which is connecting these two components. Okay. So what I'm trying to say here is that let's suppose there's a cycle in this graph. Okay, and in this graph, I have formed the MST, minimum spanning tree, which looks like this. So basically, apart from this dotted edge, okay, apart from this dotted edge, whatever I have drawn here is minimum spanning tree, which means I am saying that this is a minimum spanning tree itself, which means there is no cycle here or something. This is some other component of minimum spanning tree and so on. Okay, and suppose by contradiction I am saying that I have taken the heaviest edge. Okay, suppose I have taken the heaviest edge. Then tell me, since this heaviest edge I am saying that it was a part of a cycle. Okay, then won't there be one more path which is connecting to these two components? I mean, since this is a part of cycle. See what I'm trying to say, that let's suppose there is a cycle. Okay, let's suppose there is a cycle. I want to prove that if there is a cycle, then let's suppose this is the heaviest edge. I want to prove that this heaviest edge is not a part of any MST. Okay, so I'm assuming that all edge weights are distinct. Okay, so we can relax this assumption in a while, but for now just assume that all edge weights are distinct, which means if this is 10, then there is no other 10. Suppose other values are 1, 2, 5 and so on, right? And maybe let's suppose 3 and 9, and let's suppose this is 6 or so on, right? Now suppose this is the cycle that we have. Now my claim is that since 10 is heaviest in the cycle, hence 10 will not be part of any MST. Is the claim clear? At least 10 will not be part of any MST. Okay, let me know if the claim is clear to everyone. So what I'm saying is that if this is a heaviest edge, then this is not a part of any MST. Okay, I want to prove this. Suppose I want to prove this. Okay, let me know if the claim is clear. Okay. Now let's just prove this claim. Now I'm proving this claim using this. Okay, so I want to prove that this is not a part of any MST. I want to prove using contradiction. Okay, using contradiction I want to prove. So proof using contradiction, which means we will first assume, okay, assume 10 is part of MST, and then we will later on will say that okay, this is not possible, hence we will disprove it. Okay, so proof by contradiction means we will first assume that okay, 10 is part of MST. Now what is the problem if it is a part of MST? Okay, that's what we want to see. Let's just assume that 10 is a part of MST. Then what will happen? You will say if this is a part of MST, then since this is a part of cycle also, right? So basically let's just draw the MST. Okay, let's just draw MST where 10 is a part of MST. So what will I say? Let's suppose this is the MST that I have. Okay, this is the MST that I have drawn where 10 is a part of MST, right? Now now what I'm saying here is that since this 10 is a part of MST and since it is a part of cycle also, which means see, MST doesn't have any cycle, but which means if I have the complete graph, then there must be one more edge which is connecting like this. I mean, basically, since 10 is a part of cycle also in the complete graph, in the original graph, that is why there is one more edge. There is one more edge, right? Now, since 10 is the heaviest one, so that is why this edge must be lesser than 10. Suppose this edge is 8, 5 or something, okay? Suppose this edge is 5. So can I not remove this 10 and have this 5 and still I have the MST? Isn't it? So that is why the original was not MST. So which means if I can if I can decrease the value of MST, then how the original was the MST? What I'm trying to say here is that if 10 is a part of MST and if I draw the MST like this, then since 10 is a part of cycle also, that's why there must be one more edge which is something like this where the 10 is forming a cycle. So what I can do here is that I can remove this 10, I can bring this 5 here, which means I can say that if Emax is part of MST, okay, this is basically by contradiction I want to prove. If Emax is a part of MST, then what I can say, then let's suppose T is MST, okay, T is MST. Then what I can do, I can remove this Emax from T and bring some other E such that this whole is basically having lesser value than MST, which is not possible, right? Lesser than MST, which is not possible. Hence Emax. So basically the first thing that we have assumed, that Emax is a part of MST, it is false. Okay, so this is a proof by contradiction. You don't need to understand proof too much. I just told you the layout. So if this is a cycle and this edge is a part of MST, then what you can do, this is how we prove in most of the greedy algorithms, which means we will say that, okay, let me plug out this and let me plug in something else. Okay, so if you plug it out, and you can definitely plug in something else such that these two components, okay, these two components are still connected. That is why you will say that this 10 cannot be a part of the MST. Okay, so anyway, the result is more important. The result says, okay, so you remember this. I will ask you to remember this result because this is very important. Result is more important, which says that a heaviest edge of cycle cannot be part of any MST. Okay, is this clear to everyone? This is called cycle property. Okay, this is called cycle property. Okay, now let's just move on. So there is one more property which is called cut property. Cut property says that smallest edge crossing any cut must be part of all MSTs. Which means what is a cut here? Let me just first tell you what is a cut, and then I will tell you what is a cut property. Let me tell you, there has been GATE 2022 question, okay, GATE 2022 question, recent question, just based on these two properties, right? Okay, just based on these two properties, cut property and cycle property, there has been GATE 2022 question. Let me just tell you that what is this cut. See here, a cut is basically defined like this. So a cut is nothing but, like, let's suppose this is a graph. Then if some vertices you are putting, let's suppose this is V1, okay, in one set, and in another set you are putting another set of vertices, then this is called cut. For example, if this is a graph, then you can say this is a cut. Okay, if this is a graph, then you can say anything is a cut, where you will say that the vertices will form like this. Okay, some vertices will be in one set, another vertices will be in one set. That is called cut, right? Now, for example, if this is a graph, you can say this is a cut. Okay, for example, let's suppose if this is a graph, right? Anything. If this is a graph, then you will say this is a cut. So anything is a cut, right? Anything is a cut. You can draw like this, or maybe like this, or anything, right? So this is cut. Now what does this cut property says? It says that whatever graph you have, right? So let's suppose this is the graph. You make any cut here. Let's suppose I make a cut here. Okay. Here these two edges are getting cut, 2 and 7. So which is minimum? 2 is minimum, right? In this cut you can say 2 is minimum. So since 2 is minimum, so cut property says that in any cut, you draw any cut, whatever is the minimum edge, okay, that is part of every MST, part of all MSTs. Okay. Is this understood? For example, here, if you draw this cut, then this 4 is a part of all MSTs. So 4 must be the part of MST, right? So for example, if you draw this cut, then 1 is a part of the MST, like that, right? 1 is a part of every MST. So I hope you understood that what is a cut. Now, how many number of cuts are possible? See, I told you that what is a cut ideally is basically just set of vertices, right? Which means that if you have n vertices, v1, v2 to vn, okay. So in how many ways you can partition these vertices? The some of the vertices are here, some of the vertices are here. In how many ways you can do this partition? Tell me. Suppose these are the n vertices, and then you want to do the partition such that for example that you want to say that okay, you want to make two sets out of it. Then you will say for every vertex I have two choices, whether to put this in here or whether to put this here, right? I have two choices. So basically there are 2 power n such partitions, right? 2 power n such partitions, right? For example, let's suppose this is your graph, okay. This is v1, v2, v3. So how many cuts are possible here? One is this cut, maybe one is this cut, one is this cut, right? So seems like there are 3 cuts, okay. I mean, one is something like this, or something like this, right? So basically, let me just list down all the cuts. Maybe v1 is v1, v2, v2, v3 is one cut. Another cut could be v2 and then v1, v3. Another cut could be v3 and v1, v2, right? So these are seems to be 3 cut. But as I just told you that if you have n vertices, then everyone is having 2 choices, either to go here or to go here. So for n vertices there seems to be 2 power n choices. But here if you have 2 power n, this is 2 power 3, which is 8, but this is not 8, you just have 3. So why that is the case? The reason is that here what I'm saying is that like here we are over counting. Basically it is a combinatorics problem, but just try to understand that we are over counting here, which means if I'm writing v1 and v2, v3 here, then in this particular process we are also counting like this, okay. We are also counting v2, v3 and v1. So basically in this particular process we are counting this as one cut, this as one cut. So every cut we are counting twice, right? Every cut we are counting twice. Hence the answer is not exactly 2 power n number of cuts. The answer will be 2 power n divided by 2. So which is 2 power n minus 1. And also we will not be having empty cut, okay. So which means if there is nothing and all the vertices are here, this is not a cut, right? v1, v2, vn, if all the vertices are here, this is not a cut. So that's why this is for the empty cut. Hence the total number of cuts, okay, the total number of cut will be like this, 2 power n minus 1 minus 1. Understood? Okay. Now I hope you got the cut property. That what is the cut property? It says, see, in GATE 2022 itself, they have asked this question about the cut property, okay, and the cycle property. So what this cut property says, that simplifying the assumptions that all the edge codes are distinct, let's suppose, then the smallest edge crossing any cut must be part of all MSTs. For example, if you cut here, then let's suppose this is the smallest edge, then this must be part of all MSTs. Okay. Understood? Okay. Now, why that is the case? So let's just prove cut property. See, the proof is similar to the cycle property itself. Okay. So similar to cycle property. In the cycle property, if you remember, what did we say? We say that, okay, we proved by the contradiction, we say that, okay, let's suppose this is the MST that we have, right? This is the MST that we have. And this is the heaviest edge. Okay. We assume that this is the heaviest edge. Then we assume that this is a part of MST. Then there must be one more edge which is connecting. And since this is forming a cycle, that is why you can remove this and you can take this. Okay. Something like that we have argued in the cycle property. Here also we will do almost similar proof. Okay. So here, let's suppose I have a cut. Okay. I have a cut. And I will say in this cut, let's suppose this is the minimum edge. And for the sake of contradiction, assume this minimum edge is not part of MST. Which means there is some other edge. So basically, let's suppose this is what we are drawing the MST, right? So let's suppose this is the MST that we draw. Okay. Now that was the cut here, but this is not the minimum edge. Okay. In this cut, I have taken some other edge. Okay. So there was a minimum which I have not taken. Let's suppose minimum was 1. But suppose I have taken 3. Okay. Suppose this edge width is 3. In this cut, the minimum was 1, but I have taken 3 in this cut. And this is the minimum spanning tree that I have drawn. Okay. This is the so-called, okay. This is so-called minimum spanning tree where I am saying that, okay, in some cut, I have not taken the minimum. Okay. In this cut, I have not taken the minimum. And still I am saying this is a minimum spanning tree. Let's just see this is even possible or not. See what you can do. You can remove this. Then these two will be disconnected, isn't it? Since this is a minimum spanning tree, that is why, since it is a spanning tree or the tree itself, that is why if you remove any edge, there will be 2 components. So if you remove this particular edge, there will be 2 components, isn't it? See here, what is happening? That you have this, and for the sake of contradiction, I am saying in this cut, I have not taken the minimum, I have taken something else. Then if you remove this something else, then you will be basically having 2 different components. Okay. Then to connect these 2 components, I can definitely plug in the minimum, isn't it? I can definitely plug in the minimum, which was 1. So if you plug in the 1, then the total cost will decrease. So earlier, if I'm saying this is a minimum spanning tree, then it is actually not the minimum spanning tree because I can still decrease the cost. How? I can remove this and I can plug in some other edge, and I can say that, see, I can plug in some other edge. Hence this is not the minimum spanning tree, right? So that is why in every cut I have to take the minimum. So don't worry about it. Let me just write the result directly because this is very important result. Okay. So what this cut property says? It says that in every cut, in any cut or in every cut, in a cut you can say, in a cut, the minimum edge is part of all MSTs. Okay. If let's suppose that that this is not the part of any MST, then we have counter proved it that we can still decrease the cost. Anyway, you remember this result, right? I'm assuming here that edge weights are distinct. Okay. So edge weights are distinct. Okay. Now we have 2 properties with us. One is cycle property and one is cut property. Let me just remind you that what are these 2 properties. So the cut property says that the smallest edge crossing any cut must be part of all MSTs. Cycle property says the largest edge in any cycle is never part of any MST. Okay. And now we have proved these things. That is fine. See here that let's see with the cycle. Then does the MST exist that has all the C edges? Obviously no, right? MST cannot contain all the cycle edges, right? How can MST contain all the cycle edges? Because it will form the cycle. Or no, because it will form the cycle. Right? Which one should not be the in the MST? If not all the edges in the MST, then the maximum cost edge will not be in the MST. Okay, that is the cycle property says. Now let's just see a very important theorem. Okay, very important theorem that we need to remember to solve many PYQs. Okay, this will help. Let me just tell you that this will help to solve many PYQs, not just one or two, many PYQs. Okay, this will help to solve many PYQs. Let's just see that what is this theorem. So this theorem says that an edge is not an MST if and only if it is the unique heaviest edge in some cycle. Okay, so basically that edge is, it says that edge is not in MST. Okay, there is only one reason why edge is not in MST. It is actually very important. You will see why. Okay, this is if and only if. Okay, that edge is heaviest edge. The edge is heaviest edge in some cycle. Okay, there is only one reason. See, if some edge is in MST, then we will see that what to do. But if you want to check that if this is not in MST, okay, then there is only one reason why this is not in MST, that it must be the heaviest edge in some cycle. So you can also write it in this way. Okay, since this is by implication, you can also write in this way that the edge is in MST. Okay, the edge is in MST if and only if it is not the heaviest edge in some cycle, right? It is not the heaviest edge. Okay, I'm assuming here the edge weights are distinct. Don't worry if these are not distinct. Don't worry. We will see that how to deal with that. I'm assuming that weights are distinct. So this is extremely important to know that what is the case when edge will not be in MST. Okay, this will not be in MST if this is heaviest edge in some cycle. Okay, now let's just see that what is this Kruskal's algorithm. As you might be knowing, this Kruskal algorithm is a greedy algorithm which basically works like this. It will take the minimum, okay, then the next minimum, which means this, right? Then the next minimum, and then the next minimum. So this is the next minimum, and then the next minimum. Okay, if it is not forming a cycle, it will keep on taking, and the next minimum, right? And then this 6 is forming a cycle, right? See, in Kruskal algorithm, you can have a cycle. So this 6 is forming a cycle, right? This 6 is forming a cycle. So since this 6 is forming a cycle, that's why you will not take 6. This 7 is also forming a cycle. That's why you will not take this 7. You will take this 8. And then I think this 8 is forming a cycle or not? Yeah, this 8 is forming a cycle, right? Because okay. Sorry, this 7 is remaining itself. So you will take this 7 and then you will take 8. Okay, either this 8 or this 8, doesn't matter. You can take one of them. Okay, let's suppose this 8, and then you will if you try to take this 8, it will form a cycle. Then you will take 9, right? Okay. Okay, so this will be the MST, right? So I know that you know Kruskal's. Now, what is the algorithm that it follows? it says that you sort the edges in increasing order. So how much time you will take to sort the edges in increasing order? Tell me. Let's suppose these are the E edges you have. Then you will be taking E log E here, E log E. If you always, if you sort the edges in the increasing order, okay. And then what you do? Then you will pick the edges in that order, and you will check if you include that in MST, okay. Then it is not making a cycle, right? If it is not making a cycle, then you will include it. Now the only crux here is that how to check, okay, whether it is not making a cycle, okay. How to check this, right? And what is the time complexity of this? Can anyone tell me how to check and what is the time complexity? See, if you have the time complexity anything, let's suppose the time complexity to check the cycle is alpha, then you are running this E times, remember, right? So it will be completely, this for loop will be E alpha, right? Completely this for loop will be E alpha. If this checking the cycle time complexity is alpha, okay, then completely this for loop will be E alpha, and then Kruskal's time complexity, okay, then Kruskal's time complexity will be how much? E log E to sort, okay, see here, E log E to sort. So E log E to sort, and E alpha to check the cycle alpha time, E times, right? So checking the cycle again and again. Check if forms a cycle, right? This is to sort all edges. Let me know, is this fine? Let me know if this is fine. This is to sort all edges. This is to check if it is forming a cycle or not. So this is Kruskal's time complexity. But the question is still open, that how to check and what is the time complexity, right? So there are many ways to check. You might have heard about DFS, right? If you check using DFS, okay. See, in this, the main agenda is that how to check the cycle, right? So cycle reduction can be done using DFS. The time complexity here is V plus E, okay, V plus E, order of V plus E. So actually you can do it, but if you multiply this with E, okay, if alpha itself is V plus E, and if you multiply this with E, then this will be too much. It will be E square or something, right? It is too much time complexity. So that is why it is not a good idea to check with DFS. There is one idea, okay, that is called union find a data structure. Using this you can do it, okay. I'm not going to go to the detail of it, but here let me just tell you, this is a data structure that work incrementally, which means if you are building some minimum spanning tree, which means you keep on adding some edges, right? If you keep on adding some edges, let's suppose you add one more edge, then you add one more edge, so you're building your minimum spanning tree incrementally. In that case you apply this union find data structure. Little bit I have talked about in our course. Here interestingly, the value of alpha is just order of 1, okay. The value of alpha is just order of 1. Which means let's not go to the detail of union find data structure, but here what I'm trying to say here is that the Kruskal's time complexity will be very less now. Why? See, what does Kruskal do? Okay, let's just try to understand that what does Kruskal do. You will sort, right? You will sort all the edges, isn't it? So let me write here. See here, you will basically sort all the edges, right? And then you will pick each edge. You will just keep on checking if it is not making the cycle. If it is not making the cycle, you will include it, isn't it? Now what is the total time complexity here? See, sorting will take E log E, and suppose this is taking alpha, which I am saying just order of 1, okay, checking the cycle, suppose, okay, then it will take E alpha. This whole thing will take E alpha, right? And which will be how much? E alpha, which is just E. So what is the total time complexity of Kruskal's? It is E log E plus E. Okay, E log E plus E. Is this understood? Let me know. So basically, that's how you can find out the time complexity of Kruskal's. Now, suppose there is a question. Okay, suppose there is a question which says that we already have edges in sorted order. In sorted order. Then what is the time complexity of Kruskal's? Then time complexity of Kruskal's. Then what is the time complexity of Kruskal's? What do you think? See, if you already have, then you don't need to do this, right? Let's suppose you don't need to do this. Then this is just E, right? This is just E times cycle checking, and let's suppose cycle checking just taking order of 1. So this is just E, order of E. Okay. This is actually a gate question itself. Let me just tell you. See here. See, I think, yeah, this has been asked in gate 1992. So what they're saying, complexity of Kruskal algorithm for finding the minimum spanning tree of undirected graph containing n vertices m edges if edges are already given to be sorted. Okay, if edges are already given to be sorted, then in that case it is order of m only. Order of m. Understood? Order of m only. Okay. So this was gate 1992 question. Now let's just solve this particular question. I hope this question is visible to everyone, right? Okay. Now let's just solve this question. What they're saying is that if the Kruskal's algorithm is used for the finding minimum spanning tree of the weighted graph n vertices m edges and weights are already given in the sorted list, then what will the time complexity to compute the minimum cost spanning tree? That union and find operation take order of 1. See, union and find is one data structure that we don't need to check it. Okay. So again, what is the answer here? M or n? Order of m or n? The number of edges are m, number of vertices are n. So what is the answer? Again order of m, right? C is the answer. So answer is C. Understood? Now let's just see this. Okay. So suppose they say that you can, if edge weights of the appropriate are of appropriate values and the radix sort can be applied, which means you do not need to apply any general algorithm. You can apply the radix sort to sort. So there are some assumptions for the radix sort and counting sort, these kind of sorting algorithms, right? Which means that the edges weights should be in certain limit, okay? Which should be in order of n or something. So edge weights should be in order of n or something. So basically, let's suppose we can apply radix sort. Do you know how much time radix sort takes? How much time radix sort takes? If you want to sort m edges, then it will take order of m, okay? So here, if you are applying radix sort, if you can apply, then it will take order of m. So which means that sorting is going to take order of m. In that case, what is the final answer of the Kruskal's? In that case, just tell me what is the final answer of Kruskal's? It will be sorting is taking order of m and order of m again. So it is again order of m, right? Right? Okay, so Rajbir Rathod is asking, radix sort is hardly asked. Why we need to remember this? No, yeah, that is hardly asked, but what if they ask, right? Then you won't argue that, okay, it is hardly asked. What if they ask? Then will you argue with me? So it is better to know the things, right? So radix sort takes order of m. That's what I'm like, that is one thing that you must know, right? That is one thing that you must know. Suppose they are saying that you can apply the radix sort. In that case, the Kruskal algorithm will be taking just order of m. Okay. Okay, now tell me, can Kruskal's algorithm handle negative edges? Suppose there is a graph which is having the negative edges. Will this matter to the Kruskal's algorithm? I don't think so, right? Even if this is -3, -2 or anything, since it will just sort it, it will just check whether it is forming a cycle or not. So the negative edges and these things does not matter. So can Kruskal's algorithm handle? Yes. Okay, there is not an issue here. There is not an issue. Let's suppose we add some constant to each edge weight. Then do the MST changes? What do you think? Let's suppose we add some constant weight here. let's suppose we add some constant, which means suppose this was 3, this was 2, this is let's suppose 5, this is 9, this is 7, this is let's suppose 20, this is let's suppose 32. Okay, let's suppose these are the add weights. Now if even if you add something here, let's suppose plus 5 everywhere, will this change anything? Tell me, will this change anything? Then the answer is no, right? The MST will be same. Why? Because it will just check the relative ordering, right? The relative ordering of the edges. So earlier 2 was the minimum, now also 2 plus 5 is minimum. The relative ordering it will check. So the answer is no. Okay, answer MST doesn't change. I mean the weight of the MST will change obviously because you're adding the edges, but the MST itself won't change, right? Okay. Now let's just move to some different kind of questions, which are how many different MSTs are possible. So suppose this particular graph is given to you. Can you just tell me how many different MSTs are possible? See, using cut property, you can definitely say, see, if this is a bridge or if this is a, you can say the cut edge, right? The bridge means that it is the only edge which is connecting between these two. Then you will say that, okay, this will definitely part of MST, right? I mean, whatever you do, this will definitely the part of MST. So let me just draw it. See, this will definitely be the part of MST. Similarly, this will definitely be the part of MST. Now, as per Kruskal, you can guess that this will definitely the part of MST because Kruskal will anyway choose this, right? Kruskal will anyway choose this. So hence these two and this one is part of MST. Then what is the remaining two edges? These two edges are remaining, right? So basically you will say, sorry. So basically you will say, let me just copy this. You will say that given this graph, these particular edges are anyway part of MST, which I have just drawn, right? These particular edges are anyway part of MST. Now you want to know how many MSTs are possible. So you want to connect these two words, right? Or these two countries. You can say these two countries. Okay. Let's suppose you want to connect these two countries. Since to connect there are equal choices, like you can connect via 2 and via 2, right? So either you take this or you take this. So there are two choices here, right? There are two choices here. So you will say there are two choices. Okay. There are two choices here. So hence there are two minimum spanning trees are possible. Right? Two minimum spanning trees. I hope that is fine to everyone. Okay. Now let's just solve more questions. Let's suppose they have not given the weights and they are saying that every weight is equal. Can you tell me how many minimum spanning trees are possible here? Just tell me how many minimum spanning trees are possible here. See, in this particular graph, if you just tell me that how many minimum spanning trees are possible, then you can definitely easily tell me how. You will say that, see, this will be the part of definitely MST. This will be the part of MST, right? Which means now you will say that, see, let me just, for now, let me just, remove these edges. Okay. So basically you will say these two are definitely part of MST. Now here you were having triangle, right? You were having triangle. Here also you were having triangle. Here also you were having triangle. Now can you tell me that how many MSTs are possible? How many MSTs are possible? See, in this triangle, there are how many edges that you need to take? Two edges, right? Two edges. So basically in this triangle, you either take this and this, or maybe any two edges you can take. You can take this and this, it will connect, right? You can take this and this and so on. So basically three C2 ways or maybe three ways, right? Three ways here to select two edges. Which means in this triangle, I have three ways to select edges. These are the three ways. And similarly, in this triangle also I have three ways. So total 3 into 3, which are 9 ways in which we can select the edges, right? We can select the edges. 9 ways. Okay. So hence 9 MSTs are possible. See, there is no simple and direct formula. You need to apply the intuition. You need to apply the properties and so on. Okay. So there is no simple or the direct formula here. Let's just solve more questions and you will get to understand more. Okay. So how many minimum spanning trees are possible here? Can you tell me? In this case, how many minimum spanning trees are possible? See, this particular edge, which is here, is always part of every MST, right? This particular edge is, I think, always part of every MST. This edge is this edge. So I think these edges are anyway like part of all the MSTs. Okay. This is a cycle. You have three ways here. You have four ways here. You have three ways here. You have four ways here. So hence there are 3 into 3 into 4 into 4, which are 12 into 9, right? Sorry, 16 into 9. These many MSTs are possible, right? These many MSTs are possible because four ways here to select any of the edges, or maybe you can say four ways here to remove one of the edge, because you want to remove one of the edge, right? This is a cycle. You want to remove one of the edge. So these are the four edges. Either you remove this, or you remove this, or you remove this, or you remove this, right? Okay. So these many MSTs are possible. Okay. Now tell me how many MSTs are possible here. Just see this and tell me how many MSTs are possible here. Just let me know. See, this is also easy question. What you need to do, you just need to check that what are the certain edges. I mean, what are the edges which will definitely be there. Okay. So see, let me draw the edges which will definitely be there. See, edge per Kruskal will definitely choose this, right? And the next edge Kruskal will choose this, and the next edge Kruskal will try to choose this, but this is forming a cycle, right? Okay. And this is, since this is the only edge here, so that's why this will definitely be chosen, because this is the only edge, right? Why this is chosen? Because this is the only edge. I mean, this is, you can say, cut edge of the bridge. Bridge is always chosen, right? So bridge, this is bridge, that's why it is always chosen. And I think this is a cut here, and in the cut this is a minimum edge, right? In the cut this is a minimum edge, that's why this is always chosen. Minimum in cut, that's why it is always chosen. Okay. This is because the bridge is there. This is because the Kruskals will choose these, right? So anyway, like, I have used my intuition, I have used the properties, I have used Kruskals, I have used bridge property, I have used cut property, I have used everything, and I came out that okay, these vertices are anyway I mean connected like this. So I don't need to connect these vertices, right? These vertices are anyway connected. The only vertex that I need to connect is this, right? The only vertex that I need to connect is this. So basically, how many ways are there to connect this vertex to the remaining parties? It will depend on the edge weights. So these are the 4, 4, 4. Since this is equal, right? Edge weights are equal, so that's why these are the three ways, right? I mean, you choose using this, or using this, right? So three ways are there to connect, right? Understood? Yes, three is the answer. So which means three is the MSTs here. Yes, Mohit, that is correct. So basically, how we are getting the answer here is based on our intuition that okay, this bridge will be there, based on the Kruskals, little bit Kruskal, little bit intuition, little bit curve property, and finally you will get the answer. Okay, there is no direct way, okay, or there is no direct method. You need to use the intuition, you need to use the properties, right? Okay. Now tell me how many number of minimum spanning trees will be there. So see, Kruskal will choose this, and then Kruskal will choose this. I don't think there is any choices, right? So you will have one MST only, one MST only, right? Number of minimum spanning trees here. Can you tell me? I think Kruskal will choose this, and then Kruskal will either choose this, okay, and this is also there, right? So how many minimum spanning trees there? Can you just think about it? See, this 4 will never be the part of MST, right? I mean, you might not need it ever. So let me just do one thing. Let me go to the next page and let's just see. Okay. Meanwhile, you just give your answer that how many MSTs are possible here. So in this graph, you just see what is happening is that there is one more vertex which is B, which is connected like this. Okay. B is, let's suppose here, B and D are connected and B is connected to C. Okay. Let's suppose this is the thing. This is 4, this is 1. Can you tell me the MSTs? See, this 1 will be there, this 1 will be there. What else you can guarantee? I think A have to, if you have to connect this A, then it seems like either you can connect like this or you can connect like this, right? Okay. And this 4 is the heaviest edge in the MST. So I mean in the graph. So this 4 will never be the part of the MST, right? This 4 will never be the part of the MST. So you can definitely remove this 4 because it will not be the part of MST. And then I think now you can see that this 4 will not be the part of MST. And now if you take this 2, right? I mean there are basically, you can say these are the three choices. If you want, you can use this, right? This is one way to connect all this. This is another way. So basically these will be 3 choices, right? I mean you can just remove one of this. So these are the 3 MSTs here, 3 choices. Okay, to connect these are the 3 choices. And this 4 will not be the part of MST. Why? Because of the cycle property, right? Because of the cycle property, that the heaviest edge will not be the part of any MST. Okay. Now let's just see this. What they are saying, the minimum edge weight present edge weight is present in some MST and minimum edge weight is present in all MSTs. So is this true that minimum, if this is minimum edge weight, then it is present in all MSTs? First of all, tell me, is this true? This is false if the edge weights are basically same. Let's suppose this is minimum. If this is the case, right? If this is the case, then the minimum is not part of all MST because you anyway have to leave out one. So basically it might be the case that A, B and C are connected like this, right? This is minimum, still this is not a part of all MSTs. So hence this is false, right? Hence this is false. It is a part of some MST. Yes, you can definitely take it as a first choice. Okay, take it as first choice of Kruskal's. First edge in Kruskal. Then you can definitely make it a part of some MST, but it may not be the case that it is a part of all MSTs, right? Because edge weight might not be the distinct. But let's suppose they say that edge weights are distinct here, right? Right? I mean, in this same question, they say that edge weights are distinct. Okay. So let's suppose the question is same, but now they say that edge weights are distinct. Okay. In that case, both are true. In that case, since there is only one, then it is a part of all MSTs. Since there is only one, that is a part of all, and that is a part of some also, right? Because this is only one, then it is a part of all MSTs basically, right? Part of all MSTs. Okay. If the edge weights are distinct, if edge weights are not distinct, then it may be the case that it is not part of all MSTs, right? Is it a part of some MSTs? Yes. Yes. You can make it as a first edge in the Kruskal's. Okay. Now let's see this question, which is a very good question. It is a very good MSQ. What they are saying, this question I have taken from Berkeley University, right? You might see the link at the bottom. This question I have taken from Berkeley University. So what this question is saying, let's just try to see. This is saying that in this graph, some of the edge weights are known while some are unknown, which means this is known, this is known, this is known. Okay. And these question marks are unknown. These question marks are unknown here. What they're saying, cost of AD is 2. This cost is given, these costs are given, right? What are the that must belong to a minimum spanning tree regardless of what the unknown weights turn out to be. So they are saying in this particular graph, okay, if you take this particular graph, then which of the following is basically, this is a MSQ question and they're asking which of the following will definitely the part of the MST. Okay, which of the following will definitely be the part of MST regardless of whatever this question marks are. Tell me, GH a part of MST? GH, because this is a bridge, hence it is a part of MST, right? Yes, yes, because it is a bridge. Okay. Is BE a part of, can you be 100% sure that BE a part of MST? Okay, this is ABCD. Can you be 100% sure that BE a part of MST? BE. Tell me. Yes. Why? Why that is the case? Can anyone tell me? How you can guarantee that BE a part of every MST? Because there is a cut and this cut is having BE as a minimum. That is why, right? Yes, because of cut property. Right? Is BD, can you guarantee about BD? Can you guarantee about this BD? Anyhow? Yes, right? Again, because of the cut property. You can say that, okay, this is a cut and here the one is minimum. Yes, because of the cut property, right? Because of the cut property, you can guarantee this BD. What about this GF? GF, can you guarantee somehow? No, right? I don't think there is any guarantee you can give about the GF. It will depend on these edge weights. What if this is the highest edge weight in the cycle, right? Let's suppose this is 10, this is 3, this is 5. This is not a part of MST, right? This is not a part of MST. If this is the highest edge weight, maybe. So you cannot guarantee about this GF, but you can guarantee about this GH, this B and this C. So that is why ABC is the answer here. Okay, ABC is the answer here. This is a very good question. Okay, testing your simple knowledge. Let me know if you have understood this MSQ question. Okay. Now let's just see this. Okay, this question is true false question. Now we are moving to only questions, right? Now these are the only questions we have. There is nothing else, only the questions. So maybe if you want, I can just keep on numbering the questions. So we have started, right? The questions, let me mark the number questions from here. Let's suppose this is a question number 1, right? This is question number 2. This is question number 3. This is question number 4. This is 5. And now we are at the question number 6. Let's just see this question. Consider an undirected graph where all the edges have the weight at least 1. So now they are saying that this undirected graph, all the edge weights are at least 1. If there are exactly 2 edges with the weight 1, then any minimum spanning tree includes both of these 2 edges. So they are saying that you are having 1 and 1, exactly 2 edges with 1, and everything else is greater than 1, right? Everything else is greater, 2, 3, 5 or whatever, right? Everything else is greater than 1, exactly 2 edges with 1. Then these 2 edges are part of every MST. Then any MST include this? Is this true or false? This is true, right? EG. How? Because Kruskal will choose this and will choose this. So Kruskal will choose this and this. So there is no cycle using these 2. So you can say these 2 will be the part of every MST. Isn't it? And let me ask you here one question which has been asked in GATE also. Okay. So suppose all edge weights are distinct. All edge weights are distinct. Suppose all edge weights are distinct. Then can we claim that minimum and second minimum will be part of every MST? This is true or false? This has been asked in GATE also. Tell me this is true or false. Suppose all edge weights are distinct, then minimum and second minimum. This is true, right? True. Because minimum and second minimum will not be forming any cycle anyhow. So minimum will not be forming any cycle. Second minimum will also will not be forming any cycle. So that's why this is true. Okay. Cool. Now let's see this question number 7. Right? What they are saying is that given a graph with cost on edges and a set S, let UB be an S such that UB is the minimum cost edge between any vertex in S and any vertex B minus S. So they are saying that that let U be an edge such that UB is a minimum cost edge between any vertex in S and any vertex in V minus S, which means they are saying that there's a cut. Okay, there's a cut. Let's suppose this is S, this is V minus S, and E is the minimum. Okay, E is the minimum. Then the minimum spanning tree of G must include E. Tell me. This must be included in the MST if the all edge weights are distinct. What do you think? Then the answer is yes, right? Answer is yes. So because of the cut property. This question I have taken from MIT. This is a question from MIT, by the way. Okay, this is a question from MIT, but easy question only. So this is true, right? This is true. Now let's see. This is interesting question, which is question number 8. This is interesting question. Let's see this. So what they're saying, let G be a connected undirected graph with edge weights this. I mean, these are the integer edge weights. Suppose G has a unique minimum spanning tree. So they are saying G is having a unique minimum spanning tree. Then what can you conclude about this G? If it is having unique minimum spanning tree, then they have not given that whether the edge weights are different or edge weights are same. I mean, they are even asking this, right? Okay, then G contains no cycle. G contains at most one cycle. Can you comment anything about the cycle? Maybe let's suppose 1, 2, 3, 4, 5, 6 and so on, right? I don't think we can comment anything about the cycle. It can contain any number of cycles, even though it is having unique minimum spanning tree, right? It can contain any number of cycles. So we cannot comment about the cycles. So no. Now what about this option? All edge weights are distinct. This is interesting. See, they are saying that you have the unique MST, right? Unique MST. Since you have the unique MST, does this mean that edge weights are distinct? Edge weights are distinct. Let me give you the example here. Suppose you have this example. Okay. Suppose you have this example. Here, tell me what is the MST? MST will be this, right? Are edge weights distinct? Do you have edge weight distinct? No, right? See, interestingly, if edge weights are distinct, okay? If edge weights are distinct, then you have unique MST. This is for sure. Unique MST, right? Because Kruskals you can understand from Kruskals. But reverse is not true. Okay, reverse is not true. Which means if you have unique MST, for example, this is having unique MST, right? This is 1, 1 and 2. This doesn't mean that edge weights are distinct. Okay. So if you have unique MST, then it doesn't mean that edge weights are distinct. So hence, they are saying that you have the unique MST, right? Does this mean that all edge weights are different? Then it doesn't mean, right? So that's why D is the answer here. D is the answer here. Okay. So this is interesting question, right? And D is the answer here. This was the question number 8. Okay. Let's just see more questions. Let's see this question. Let's just name it question number 9. What they are saying, consider an undirected graph G with unique positive weights. Suppose it has a minimum spanning tree. If we square all the edge weights and compute the minimum spanning tree again, do we still get the same tree structure? So earlier, whatever tree you were getting, okay, let's suppose this is the tree that you were getting. If you square in the original graph, if you square all the edge weights, then will you be getting the same tree? Tell me. The answer is yes. See, earlier, let's suppose I said like 2 and 2 is greater than 1, or maybe let's suppose 5 is greater than 3. Then even if you square, then 25, the relationship will be still, the relative relationship will still be holding, right? So that is true. But suppose earlier you said, for example, that 3 is greater than, let's suppose, -4, but you square them, okay, you square them. Then does the relationship still hold? Does the relationship still hold? The answer is no, right? If there is a negative edge weight, then the relationship may not still hold. This is the problem. But if there is a unique positive weights only, right? Positive weights only, then the relationship will be holding. So if x is greater than y, or any number is greater than any other number, if these both are positive, you square them, again the relationship will hold. So that is why it is true. Otherwise it could have been false. Let's suppose they ask you the same question. But they say this: unique weights, unique integer weights. They say this. Then tell me. Then it will become false, right? In that case, it will become false. If this is unique integer weights, then in that case, it will become false. Understood? But if this is a positive weight, if this is a positive edge weight, then this is a true. Okay. Now let's see this question, which is I think question number 9 or 10. This is question number 10. Okay. Now let's just see this question, which is question number 10. This question is from MIT. Okay. Let's just see what they are saying. If G has a cycle and there is a unique edge E which has minimum weight on this cycle, then E must be part of every MST. They are saying that G has a cycle and E is an edge which is minimum. See, what is the cycle property? Cycle property says that if it is maximum, then it is part of, it is not a part of, okay, not part. Cycle property says if it is maximum, it is not a part of any MST. They are saying if it is minimum, okay, unique edge E, there is a unique edge E which is a minimum in the cycle, which means maybe it is the case that you are having, let's suppose 3, 4, 5. Okay, so let's suppose you are having 3, 4, 5. Let's suppose this is the case that you are having. Then they are asking this 3 is a part of all MSTs, part of every MST. Is this true? Is this true? This is extremely interesting, and let me just tell you, this is also the GATE question. GATE has directly copied this question from MIT. This is also the GATE question. We will solve the GATE questions. I'm just telling you in advance that this is also the GATE question. GATE has directly copied this question from MIT. Directly copy from MIT. Okay. Tell me, is this 3? Okay, I have not drawn the all the edges. Maybe there are all the other edges. But if this 3 is the minimum edge weight in one cycle, okay. See, this is not a theorem. This is not a cycle theorem. This is not a cut theorem. Okay, cut property or the cycle property. Okay, they are saying that 3 is a minimum here. Then it is a part of every MST. Interestingly, answer is no. The reason is that this is 3, which is a minimum here, that is for sure. But it could be maximum in other thing, right? Maximum in the other cycle. Minimum in this cycle, that is for sure. But it could be maximum in other cycle, which means this could be 1 and this could be 2. So if this is a maximum in other cycle, that's why it is a part of no MST. Okay, cannot be part of any MST. Cannot be part of any MST because of the cycle property. Right? This is very interesting question which I have taken from MIT. And also this question has been asked in GATE. Right? So this particular question has been asked in GATE. This particular question is basically from MIT, and I have also put this question in our test series. So this question is also from Go Classes test series, you can say. Okay, this question is seen multiple places. This is a GATE question which has been copied from MIT. Understood that it cannot be part of any MST. So the thing here is that this minimum could be maximum of other cycle, of some other cycle. Understood? Let me know if you found this particular question interesting. See here, this is false. Consider the graph of a tetrahedron where the three edges of the base are 1, 2, 3, 4. That's what they are saying, I think. 2, 3, 4. Right? And the three edges peak to base all the weights 1. So basically, these all are the weights 1. Okay. So basically, we have seen that this 2 cannot be part of any MST. Now let's just see this question. This question I have taken from UCSD University. So what they are saying, let G be a connected undirected graph with distinct positive weights, right? And let E be the edge. Edge E is basically UB, does not belong to an MST of G if and only if. So they have given a very strong condition. They are saying E is not in MST. If and only if this V and W be joined by a path consisting entirely of the edges are cheaper than E. Okay, I think this is U and V. So they are saying that there is an edge E, okay, between U and V. That is not an MST if and only if you have some other path connecting U and V entirely, okay. So they are saying that this is U, this is V. This edge is not an MST if and only if there is some other path connecting U and V such that all the edges here are lesser than U and V. Which means whatever is the edge weight here, okay, maybe 10, then all the edge weights which are which is in the path of U and V, okay, all the edge weights here are basically lesser than 10. If that is the case, then this is not the part of MST. Basically, yes, right? This is actually the cycle property. They have, cycle property, you can say, cycle property. They have just given the cycle property in some other form, right? Instead of directly saying cycle, they are saying, okay, there is some other path. They have just twisted the words, right? They have just twisted the words, okay? So all edge weights are distinct and they have just twisted the words joined by the path consisting entirely of the edges which are cheaper than E. So this is a cycle property only, right? So the answer is true. Okay. Let me know if you have understood this question. This was the question number 11. Let's just solve question number 12. Let's just solve this question. So what they're saying, if an edge E is not a part of any MST, then it must be maximum edge weight of some cycle. What do you think? It is not a part of any MST. Then it must be the maximum edge weight of some cycle. Yes, that is what we know, right? That is a cycle property or something. So some edge is not a part of any MST because it is a heaviest or the maximum weight edge in some cycle, right? So that is why it is true, right? This is the cycle property. Okay. So let's just see this question number 13. Okay, this question number 13. So what they're saying, suppose the edge weights are non-negative, then the shortest path between two vertices must be part of some MST. So they are saying that let's suppose the edge weights are non-negative, then the shortest path must be part of the MST. Suppose this is 7, this is 5, this is 5. So can you tell me the shortest path between A and C? What is the shortest path between A and C? I think 7, right? The shortest path between two vertices must be the part of some MST. Is this the part of MST? What is the MST? MST is this only, right? MST is this. So is this 7 is part of MST? The answer is no, right? So 7 is not part of MST. So hence, this is false. This question is again from MIT. This is false. Okay. Now let's just see this. So true or false? Edge with minimum weight in G is in some minimum spanning tree. What do you think? If this is a minimum weight, then it will be at least in some minimum spanning tree. Okay, don't worry about whether the edge weights are distinct or not, but at least it will be in some minimum spanning tree. What do you think? Yes, right. This is true because you can always choose this as a first edge in the Kruskals. That's why this is true. This is question number 14. Let T be any MST and E belongs to this. Show that there exists a cut such that E is minimum edge across this cut. So they are saying that let's consider a MST, okay, which is T. Let's suppose this is a MST which is T, and E belongs to T such that E is also in the cut. Let's suppose this is E, such that E is minimum edge across this cut. Okay, they are saying show that. Okay, this is not directly true false. So I mean this is just a cut property, right? This is just a cut property. This is not directly true false because I have not modified it with the language. They're saying show that. So they're just asking to prove the cut property itself. Okay. So if you remove this, then you can see this. Let T be the MST, and then there exists a cut such that E be the minimum edge across this cut. So you can definitely show it, right? If this is MST, then you can pick any edge E, and you can say that it must be the minimum across this cut. Okay, there exists a cut. So basically, this is a cut property only. Now, anyway, let's just see this question, which is question number 15, right? This is question number 15. So what they are saying, given a connected graph G with the positive weights, which of the following will compute the MST of G? Change the weight of each edge from CE, okay? I mean the cost of edge to, if you add, then this is okay. Is this okay? Yeah, relative ordering will be same, right? Earlier, if x is greater than y, and if you add it, right? If you add, then also the relative order will be same, right? X plus 17 also greater than y plus 17. What about multiply? Yes, right. So if you multiply earlier if x is greater than y, then after multiplication 17 into x is also greater than, right? Let me just write it. See, earlier, see in case of MST, the relative ordering should be same, right? Across the edges. So if earlier x is greater than y, then here x plus 17 is also greater than y plus 17. 17x is also greater than obviously 17y. You can cut this 17. Here also you can cut this 17, right? Okay. Change the weight of each edge from, you square it. We have already seen if it is a positive weights, then square is okay, right? Then square is also okay. We have already seen if it is a positive weight, then square is okay. So that's why all of the above is the answer here. All of the above is the answer, right? Okay. Now let's see this question. What they are saying, consider these two statements, S1 and S2. Suppose T is the shortest path tree using the register algorithm. After adding C greater than 0, every edge in the graph, T is still the shortest path. Okay, we have already seen this, right? So this is no. I mean, in the previous lectures, we have already seen this. The shortest path might change, right? Why? Let me just tell you. See, if you add something, then shortest path might change. The reason is very simple. Suppose earlier this is the shortest path. Let's suppose this was 1, 1, 1, right? And this was, let's suppose, 5. So earlier, if this is the shortest path, then if you add, let's suppose some number, okay? If you add, let's suppose 3, okay? Then the shortest path will change or not? Tell me. So if you add, let's suppose 3, right? plus 3, plus 3, plus 3, plus 3. Then tell me the shortest path. Now the new shortest path, see here it will be 12, right? It is just 9, it is just 8. So this is the new shortest path, right? This is a new shortest path. So if you add something, then shortest path may change, right? But the MST won't change. We have seen. So earlier if the MST is this, now also the MST is this, right? MST won't change, but the shortest path may change. The heaviest edge in the graph cannot be the part of minimum spanning tree. What do you think? The heaviest edge? No, it can be, right? So if let's suppose this is 1, 2, this is the heaviest edge, and if it is a bridge, what if it is a bridge, right? The heaviest edge, what if it is a bridge? So cannot be the part of any MST? No, that's wrong. So that's why this is wrong. T is still the shortest path. This is also wrong. So both are false, right? Both are false. Okay. This is easy question only. Both are false. So answer is D. Right? Okay. Now let's see this question. Consider these two statements. Given a weighted directed graph with distinct weights, the shortest path between any two vertices will be unique. Given a weighted directed graph with the distinct weights. So do you think the shortest path will be unique if the weights are distinct? No, right? It can be like this, 1, 2, and then this could be 3. So there are two shortest paths between these two vertices, right? There are two shortest paths. So that is why this is false. This is false. Why? Because there can be two shortest paths like this. So suppose this is 1, and this, sorry, the weights are distinct. So let's suppose this is 1, 2, 3. So here two shortest path, right? Two shortest path. A MST cannot contain negative edges. No, it can, right? It can. So this is false. This is false. So that's why again D is the answer, right? Again D is the answer. Sorry, given a weighted, so they are saying B. Given a weighted directed graph with distinct weights, the shortest path between any two vertices will be unique. So this is a weighted directed graph, weighted directed, right? With a distinct weight. No, the shortest path, I think there is a misprinting. The shortest path need not to be unique. So that's why this is also false, this is also false, because the shortest path here between two vertices is not unique. The shortest path between two vertices will be unique. No, it need not to be, right? So that's why this is false, this is also false. Okay. Let's see this. So we have lost the count of the question numbers, but that's fine. 15, this is 16, this is 17, and now this is question number 18. Let's see this. What they are saying. To find the shortest path for a graph with negative weights, we can eliminate negative edges by adding the large enough constant to every edge. Okay, so they are saying that you can add, let's suppose there is some negative edge, then you can add and then you can find the shortest path. So we have seen that addition may change the shortest path itself, right? So that's why it is false, right? So because addition may change the shortest path itself. Now what is this? Let T be the MST for any arbitrary edge. There exists a cut such that E is minimum across this cut. So suppose you pick some edge. Now they are saying you pick some edge in the MST, okay? Then there must be existing some cut such that this E is a part of is a minimum in that cut. So what do you think? This is correct, right? Okay, let me check the previous question. So why the answer is B? Oh, sorry, MST can contain. This is like can contain. Okay, yeah, this is true. I have read it cannot. Okay, I misread it. I thought it is written right. It is written cannot. Okay, I misread it. So this is true. and this is false. So S1 is wrong and S2 is correct. Yeah, B is the answer. Yes. So I think I have misread it. I read it cannot. Okay, I read it cannot. And MST can contain. So that's why B is the answer. Yes. So that's correct. B is the answer. Okay. Cool. So here they are saying that you pick some edge from the tree, then you can say there must exist some cut such that this E is a minimum in that cut. Then the answer is yes, that is true, right? So this is true. S2 is again correct and S1 is false. So that's why B is the answer here. Okay, B is the answer. Now that was question number 18. This is question number 19. Let's just see this. What they're saying, to solve a single source shortest path problem for a graph with no negative weight edge. Okay, there is no negative edge weights. It is necessary that some edge can be relaxed twice. Okay, so this is a part of Dijkstra. Okay, if you have seen the Dijkstra algorithm, then you will say that okay, Dijkstra do two things. It will see Dijkstra for any graph. What does Dijkstra do? It will extract the minimum. Okay, whatever is the minimum, it will extract that minimum, right? It will extract that minimum and will relax all the outgoing edges, right? Will relax all the outgoing edges. So any outgoing edge will be relaxed just once. Okay, so any outgoing edge will be relaxed just once. Why? I mean, at most once, basically. Okay, why that is the case? Because you will be relaxing this edge only when you are taking out this from the priority queue, or you are extracting that from the priority queue. Then only you will be relaxing all the outgoing edges, right? So let's suppose this is already final. I mean, this is already out of the priority queue. What I'm trying to say is that suppose there is a graph something like this. This is 1, this is 2, let's suppose this is S. Okay, and then maybe let's suppose this is 3. Let's suppose this is the graph that you have. Now what does Dijkstra do? It will first pick this, it will relax all the outgoing edges. So it will relax this, right? And it will also relax this. Okay, so it will relax all the outgoing edges. Now sorry, let's suppose this is 2, this is okay, just for the example. So what Dijkstra will do? It will pick this and it will relax all the outgoing edges. Now the weight of everything will be initially infinity, but after relaxation it will be 1, it will be 2. Let me know if that is fine, right? That's what the Dijkstra does. Okay. Now what will happen? See, now what will happen? That you will pick the next minimum among 1, 2 and infinity. What is the next minimum? Next minimum is this one, right? So you will say, okay, let me pick it. Let me relax all the outgoing edges. Okay. Now you will relax this edge, this outgoing edge. You will also relax this outgoing edge. So basically, you will relax these two. Are you going to relax this? No, because this has already been relaxed, and anyway, this is going to the final. Okay, so you will relax this and you will relax this. So that's why this is 4 and you will relax this, but it will not get updated. Now you will choose the next minimum, which is 2, and then you will relax this. So here in this example, you can see that you are relaxing every edge only when you are picking it, right? I mean the outgoing edge only when you are picking it. Now you are relaxing this edge once you pick this, you're relaxing this edge once you pick this. So every edge we are relaxing just once. Okay, and obviously there is there might be the case that we are relaxing some edge maybe 0 times. So maybe let's suppose I have something like this. So let me give you the example where I'm relaxing 0 times. I mean one of the edge 0 times. So first you will take this, you will relax this. Let's suppose you will relax all the outgoing edge of this. Yeah. Yeah. Let's pick this example. See here, let's suppose you have this example, right? Now what you will do, you will pick this, you will relax these two, right? You will relax these two. Now this will be 1, this will be 2. Now you will pick this, you will relax this. This will be 6. Now next which one you will pick? You will pick this, right? You will pick this. Sorry, in this case also, I think we are relaxing this edge. Like I want to construct an example where I'm not relaxing one of the edge anytime because it is already final. Okay. Okay, maybe you can consider this a directed edge. Okay, maybe this you can consider this a directed graph or something. Okay, then if you pick this, then you will be not be relaxing any edge because there is no outgoing edge here, right? Then you are going to pick this. Then tell me, are you going to relax this edge? Let's suppose this edge cost could be anything. Okay, let's suppose this edge cost is 5, 3 or anything. Then you will not relax this because the moment you are picking this, then it is already going to the final. So some of the edges you might not even relax, and any edge you will relax at most once. Okay, so we have already seen this in the previous lecture. That's why I'm not going in the more detail. So basically in the Digestra you can say at most one time you will relax. Okay. Prim's and Kruskal algorithm still work if the edge weights are not allowed to be negative. Yes, it is correct, right? It is correct. And what they are saying is sort of problem graph with no negative edge weights. It is necessary that some edge weight can be relaxed twice. No, that's wrong. So that's wrong. That is correct. So S2 is correct and S1 is wrong. So again, B is the answer, right? Okay. Now let's see this question, which is question number I think 20. Right. This is question number 20. Let's see this question, what they are saying. The first edge edged by the Kruskal can be the last edge be the Prim's algorithm. Is this true? Just think about it. They are saying the first edge you add in the Kruskal could be the last edge in the Prim's. See, Prim's says that, let's suppose this is ABC. Let's suppose this is 1, this is 2. If you apply the Kruskal, Kruskal will choose this as the first edge. Can this be the last edge in the Prim's? Yes, if you start Prim's from C, okay, start Prim's from here. Then Prim's will first take this, then this, right? So the first edge in the Kruskals can be the last edge, yes. Can be the last edge, yes. In the Prim's. In a graph, if one raises the length of all edges to the power 3, then the minimum spanning tree will be same. What do you think? In a graph, if the length of the edges, so basically they are saying if x is greater than y, then is this also true? The 3 power x is greater than 3 power y. What do you think? So if x is greater than y, which means the relative ordering, they are saying the relative ordering won't change. That is true, right? That is true. Because this exponential or this 3 is basically the increasing function, right? It won't change the relative order. So that's why this is also true. Because it is a increasing functions basically don't change the relative orders. Okay. The heaviest edge in the graph cannot belong to the minimum spanning tree. No, it can belong if it is a bridge. So that's why it is false. The maximum spanning tree of the maximum cost. Okay, instead of the minimum spanning tree, they are saying the maximum spanning tree can be computed by negating the cost of all edges in the graph and then computing minimum spanning tree. So they are saying that if you want to compute the maximum spanning tree, okay, if you want to compute the maximum spanning tree, then what you can do is basically you negate all the edges, which means if this is 5, this is 10, this is 3, this is 2, this is 1, then you first put minus everywhere, then you find the minimum spanning tree. Okay, then yes, we can do this. Basically, now if you find the minimum, it will be the maximum. I mean, it is the minimum edge, right? It is the minimum edge. The next minimum is this, the next minimum is this, and the next, sorry, the next minimum is this. So yeah, this, and the next minimum is this, right? So basically, if you do this, then you can definitely find, ultimately you will be having this, and the structure is same as the maximum spanning tree, right? So this will be same as the maximum spanning tree. So what is the answer here? This is also true. So I think A, B, D are the answers, right? True, true, and true. Okay, this works, and none of the proof of the MST depend on the edge weight being the non-negative. Yeah, it could be in the MST, the edge weight could be negative or the positive also. Okay, so A, B, D are the correct answers here. Let's just see this. Okay. So this is related to Dijkstra. Do you remember the Dijkstra algorithm? So in Dijkstra, we do what? We do like this. We do extract min and relax edge, right? Relax outgoing edge. That's what we keep on doing it, outgoing edge. So as far as in Dijkstra, as far as every vertex is concerned, okay? Every vertex is concerned in Dijkstra. As far as every vertex is concerned, it basically get, you can say extract, okay? You extract every vertex, extract once, right? Which is also called as delete min. Delete min. Every vertex will be deleted just once. So for every vertex, you can say it is a delete min. And whenever, I mean, if you talk about every edge, then at most one time relaxation will be there for every edge, right? At most one time relaxation will be there. So you will, relaxation is also called relax at most one time. Can anyone tell me relaxation means? In terms of heap terminology, the relaxation, basically relax is nothing but updating the priority, right? Updating the priority, maybe to something else, right? Du plus v or some weight or something. Updating the priority basically, right? If you are using heap, this is called as decrease key. Okay, this is called as decrease key. So as far as every vertex is concerned, there is a delete min exactly once. So v times you will be doing delete min, right? Delete min will be taking log v time because the heap is consisting v vertices, and decrease key will be taking how much time? So e times you will be doing decrease key. So decrease key will again be taking log v time, right? Okay. So this is the time complexity of Dijkstra. If you are using, if you are not using adjacency matrix, basically if you are using adjacency list, okay. So let me just write it here. Anyway, we can have one session about the Dijkstra and the Bellman fold which is remaining. We can have one session. I'm just telling you quickly here that using heap plus adjacency list. Okay. So what they're saying, that assume that you are given a magical priority queue or the magical heap data structure which perform extract, min, insert and decrease key in order of one only. See, you need to do v times delete min in Dijkstra, delete min, and e times you need to do decrease key, right? So they are saying there is a magical priority queue which can do delete min and the decrease key in order of one only. Then you can implement Dijkstra algorithm to run in order of v time, v plus e. Yes, that is true, right? That is true. If this is 1, then it will be just v plus e, right? So that's why it is true. What about this? Let's see a cycle of this graph G with distinct cost. Let edge E be the cheapest edge belonging to C, right? So they are saying that in a cycle, I think we have already seen this particular statement from MIT. Can you tell me whether this is true or false? I told you this is from the MIT question. This has also been asked in GATE, right? This has also been asked in GATE. So what they're saying, that if CBS any cycle end with the distinct edge cost, let E be the edge with the cheapest. Okay, in the cycle, if it is cheapest, then it belongs to the minimum spanning tree. See, in the cycle, let's suppose it is cheapest. Maybe it is 3, 4, 5, and this 3 is cheapest. But this cheapest could be the costliest in other cycle also, right? This is 1, 2. That is a problem. Then it is not part of any MST. We have seen this, not part of any MST. So that's why this is false. So this is false, right? So S1 is true and S2 is false. So A is the correct answer here. S1 is true, S2 is false, right? Okay. Now let's just see most interesting part of this particular lecture, which is basically, let me just go to that slide, which is finding the missing edge weights in MST. This is most interesting and most important. Right? Most important and most interesting. Okay, let's just see that finding missing edge weights in the MST. So there will be two kinds of problem. What they will give you some MST. Okay, they will give you the MST. I will solve the gate question, TIFR question, and every other question. So basically there has been the gate questions, there has been the TIFR questions, right? So there has been many questions regarding this particular concept. So what they will give you some MST, right? And then they will say that okay, these edge weights are forming the MST. Then they will, let's suppose they will say that there are some other edge weights which are not the part of MST. Maybe this edge weight is not a part of MST, this is not a part of MST, and so on. Then they will say that okay, that what is the cost of this? I mean, this is one kind of question that they will miss the edge weight of the edge which is not part of MST. They might miss the edge weight of the edge which is a part of MST. So there are basically two type of questions. Okay, the first kind of problem will be unknown weights in the MST. The second kind of problem will be the unknown weights outside the MST. Let's just see that how we can solve this particular these type of questions, right? Okay, so let's see this question directly, which I have taken from Cornell University. What they are saying, I think this question number, if I talk about the question number, then we have lost the track. This is 20, 21. Okay, I think this is probably question number 22. So what they're saying, that for the following graph, the both edges form the bold edges. Okay, the bold edges. I think this is the bold edge. 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 They are saying these edges are basically forming the minimum spanning tree. Okay, then what can you tell about the range of X? So maybe the minimum or the maximum. So what are the minimum or maximum possible values of X? So basically this is lying under the case 1, where they are asking the edge cost of something which is a part of MST. Okay, anyway, let's not worry about it. I'm just telling you that they are asking about the case 1. Okay, so let's just solve this question. They are saying that what are the values possible for X. Now what we will do, see, we will first draw the MST. This is the MST that we have, and I'm just removing all the edges, right? I'm removing all the edges. I'm just drawing the MST. Okay. Now you do one thing. You basically, what you do, you keep on plugging one values. So basically you bring one non-MST edge here. If you bring one non-MST, let's suppose you bring this 20. Then what can you say here? Is this 20? Tell me, everyone, please tell me, is this 20 forming cycle with X? Is this 20 forming cycle with X? See, this is a non-MST edge. Okay, this is a non-MST edge. And this edge is in the MST. This edge, everything else is the part of MST. This is the non-MST edge. You just tell me, is this 20 forming the cycle with X? If the answer is yes, then what can you say about this non-MST edge or this edge weight? What can you say? Tell me. see here, this 20 is forming the cycle, right? This 20 is forming a cycle. Then you can say that x must be lesser than or equal to 20. It cannot be greater than 20. See, if x is greater than 20, which means, let's suppose, if x is 21, if x is 21, then can it be the part of the MST? See, it will be the highest, right? In that case, it will be the highest edge. Since it is a part of MST, it has to be lesser than or equal to the highest. Since it is a part of MST. So that's why x must be lesser than or equal to 20. Why? Because it is a part of MST, that's why it must be the lesser than or equal to the highest. Okay. So what I'm trying to say here is that, see, that let's suppose you are having this as x, right? This x, I want to find out the value of x. What I did, let me write down the steps. Okay, what I did as a step 1, draw MST, right, which was like this, right? That was the step 1. Now once the step 1 is completed, now what is the step 2? Step 2 is basically bring non-MST edges, okay, one by one. Step 2, bring non-MST edge and see if it is forming a cycle. Bring non-MST edge and see if it is forming a cycle. Yeah, we will see all other edges, right? And see if it forms a cycle. Okay. We will see other edges also. See, if you bring this 20, is this 20 forming a cycle? If yes, then you write this inequality. Okay, then you write this inequality if this 20 is forming a cycle. Now you remove this 20, I mean this 20 is done. Now you bring some more non-MST edge. Okay, just one some other non-MST edge. Can you bring some other non-MST edge? So you can bring 7 also, right? You can bring 7 also. Is this 7 forming a cycle with x? This 7 is there. It is forming a cycle, but not with x. So 7 is okay, but 7 is useless to me. 7 is not helping me anywhere. Okay, I mean 7 is good. 7 is forming a cycle, but not with x. So can you write x is less than or equal to 7? No, I cannot claim something like this. Okay, because 7 is not forming a cycle with x. That's okay. So 7 and 20 is done, right? 20 was useful to make some inequality. 7 was not useful, but that's okay. Now bring 9. Is 9 forming a cycle with x? Tell me, 9 forming a cycle with x? If yes, then you write it, okay? You write it, okay? Which is x less than or equal to 9 also. Why? Because 9 is forming a cycle with x. If 9, see, this is a cycle with x. So if this is forming a cycle, then x, first of all, x cannot be the heaviest edge here. So x cannot be greater than 9, right? X cannot be 10. Can x be 10? No, because of the cycle property. X cannot be 10. X cannot be the heaviest edge here. That's the thing. So it must be less than or equal to 9 only. It cannot be 9.1 even, right? It cannot be the heaviest edge. So it must be 9 only, right? I mean less than or equal to 9. Okay. You bring some more edge. You 7 is done, 20 is done, 9 is done. Okay. Just bring the last edge, which is 10. Is 10 forming cycle with x? So I think 10 is not forming a cycle with x, right? So 10 is also not helping me. That is fine. So you got two inequalities. Using these two inequalities, you can say x is less than or equal to 9. Right? X is less than or equal to 9. Is this clear to everyone that how we are finding this x? How we are finding the range of this x? X is less than or equal to 9. Okay. Cool. So I hope you understood that how to do this question. Now let's just do more questions, right? See solution, x is less than or equal to 9. By the way, this question is from the Cornell University, okay? This question is from Cornell University, which is extremely reputed university. Let's just see other questions. Let's see this question which I have taken from Berkeley University, okay? This question which I have taken is from Berkeley University. Let's see what this question is saying. They are saying that for this graph below, let x be the unknown weight of edge DE. Edge DE, it is having x, right? It is having x. Can the mark edges in the bold be the valid minimum spanning tree? So they are saying that if this is a valid minimum spanning tree, then what is the value of x? What are the values of x? Okay. So they have given the valid minimum spanning tree, something like this. Okay. See, what is the difference between this question and earlier question? The difference is that in this question, they are asking about something which is not a part of MST, right? See, earlier they asked X. The X was part of MST. See, earlier they asked X, and the X is a part of MST. Okay. Now they are asking this X, which is not a part of MST. So this is lying under case 2, where the missing edge, okay, or the missing weight is not a part of MST. Okay. The missing edge weight is not a part of MST. Okay. Now this is case 2. If this is MST, then can you do this? See, see, there are two cases, right? Let me just remind you that first kind of problem will be unknown weights is in MST. Second kind of problem will be unknown weights will not be in MST. If unknown weight is in MST, then we have seen how to do, right? So what we will do, we will say that, okay, we will keep on bringing the non-MST edges, right? We will keep on bringing one by one only, okay? We will keep on bringing the non-MST edges. And the second kind of problem is that unknown weights is outside MST. In this, what we will do, that pick any edge E of unknown weight. If we add E to the MST, it will create a unique simple cycle. All the edges of MST must be lighter than this. So collect all the inequalities, all of this form, where X is the unknown weight of E and A is a known number. Repeat until we have gone through all such edges of E unknown weights. Now we have the collection of inequalities where unknown and the numbers remove the redundant inequality. Okay, let me just tell you what they are trying to say. Is basically, see here, we want to find out this X, right? Now what you need to do, see, this is not an MST. If and only if this is the heaviest edge, isn't it? Heaviest edge in some cycle. Now what you do, you just tell me which cycle it is forming. This is forming this cycle. So can you tell me that what should be the value of X? It should be the heaviest edge, right? Should be the heaviest edge in that cycle. So what should be the value of X? Just let me know. Just try to solve this question and let me know that what are the values of X that you can write here. See, the cycle it is forming, okay, with the X, the cycle it is forming is basically the heaviest is 2. So X cannot be lesser than 2, isn't it? See, this X, it cannot be lesser than 2. Why? The moment it is lesser than 2, then it is forming a cycle with this, then 2 cannot be the part of MST. So X must be the heaviest on the cycle, right? X must be the heaviest, which means X must be greater than or equal to 2. It can be 2. If there are multiple 2's, maybe I have chosen to go with this, right? Maybe I have chosen to go with this. That's fine. It can be equal to 2, but it cannot be lesser than 2. So X must be greater than or equal to 2. Right? Okay. Why? Because X must be heaviest in the cycle. So here we have not done multiple things. This is just one time. See, earlier what we have to do in this case, if this is the MST edge which is missing, right, then we have to keep on plugging, check, okay, if with 12 check, with 7 check, and so on, right? But here we do not need to do it again and again. Just one time plug in and see what is the heaviest here, right? That's all. Okay, let's solve more questions. You will see here the answer is greater than or equal to 2. Let's solve more questions. You will get to understand more. So let's see this question. What they are saying? They are saying that in the graph above, a certain minimal spanning tree comprises of X, Y, and Z, as well as 7 other edges. So they are saying this is X, Y, and Z. So minimum spanning tree. They are saying the minimum spanning tree already have X, Y, and Z. And 7 other edge. Why 7 edge? Because this is 3 and 3, 6, 9, 11. So 11 minus 1. So basically there are 10 edges because in the MST, because these are the 11 vertices. So out of 10, XYZ is already there and 7 other. Okay, XYZ is already there and 7 other. That's what they are saying. Now list the weights of 7 edges in MST other than XYZ. So they are saying other than XYZ, what are the edge weights that must be there? Okay. See, this X, see, let's just apply Kruskals. Okay. Let's just apply Kruskals. Let me just apply Kruskals and let me tell you what are the other edges that will be there. See, seven other will be there, right? 1, 2, 3, 4, 5, 6, and 7, right? So 7 other will be there. That is for sure. Now, the only thing is that we need to ask that which 7, right? See, let's just apply Kruskal's. So out of all of this, which one is minimum? 10 is minimum. Now you can say maybe X is minimum, maybe Y is minimum, maybe Z is minimum. Maybe, actually, maybe X, Y, Z, maybe I have chosen, okay? Maybe even before 10, maybe after 10, maybe here, maybe here, maybe here, maybe here X, maybe here Y, maybe here Z, or so on, right? Let's not worry about it. I'm just writing the remaining 7 edges, right? Okay. As long as this 10 is not forming a cycle with X, Y, Z, it's fine to me, right? I can definitely take it. So 10. So 10 is done. What is the next minimum? The next minimum is, I think, 30. So 30 is also done. And then the next minimum is, I think, 40. Sorry, next minimum was 20. After 10, it was 20. Right? It was 20. After 10, it was 20. And then it was 30. Right? It was 30. See, as long as this 30 is not making a cycle with this 10, X, Y, Z or anything, right? So I can definitely take this 30. And then what next? This 40 and this 50. Is this 50 forming a cycle? No, right? Okay, so I think, yeah. And then what next? 60. Where is 60? 60 is forming a cycle. So you will not take 60, right? You will not take 60 because 60 is forming a cycle. That's interesting. See, you will not take 60. Why? Because Y is already in the minimum spanning tree which is given. So that's why 60 you will not write here, right? 60 you will not write here because it is forming a cycle with Y. What about 70? Is 70 forming a cycle? Okay, so let's just check. No, right? So I think you can take 70. What about other 80? Is 80 forming a cycle? Tell me. I think 80 is forming a cycle, right? So that's why you will not take 80. What about 90? Is 90 forming a cycle? Yes, right? So I think 90 is also forming a cycle. This big cycle 90 is forming. So that's why no. What about, okay, 100? 100 is also forming a cycle. So here I think we need to go with 110, right? Okay. 10, 20, 30, 40, 50, 70 and 110. Right? So this is the answer. Let me know if you have understood this. Easy question only. It's not very hard question. Okay. So, so this is easy question. Now let's just move to the next question. What they're saying, the value of edge with X could be 120. So this is true or false? This particular X, can it be 120? Can it be 120? Tell me. See, our minimum spanning tree is 10, 20, 30. Let me even make the minimum spanning tree. 10 and then 20 and then 30. Right? 10, 20, 30 and then 40 and then 50 and then 70 and 110. This is 110, this is 70. Now tell me the value of this X. The could be 120. Okay, just tell me the range of this X. We will see if it is 120 or not. Okay. See here, what is the non-MST edge? So now we have the MST, right? So this is the MST that we have. Now what we can do, we need to find out the value of X, right? X, Y, Z. So suppose we need to find out the value of X, Y, Z here. Let's just find out the values of X, Y, Z itself. So for that, we will first have the MST. We will draw the MST. This is the very first step that we need to do. Okay. We will draw the MST. And now you tell me, what are the possible values of this X? See, if you see, these are the 1, 2 and and 3, right? 3 and the 4. Okay, these are the 4 edges which are in non-MST. Okay, so let me just remove this also. Yeah, these are the 4 edges. Now let's just keep on bringing. So if you bring 120, will this impact anything to X? Tell me, if you bring 120, will this impact anything to X? I think no. 120 will not impact anything. If you bring this, it will not form a cycle, right? It will not form a cycle. So 120 will not form a cycle. What next? This 100, this 90, this 80. Okay, let's just check with 90. If you bring this 90, is this forming a cycle with X? I think this is forming a cycle with X, right? Since this is forming a cycle with X, so X cannot be greater than the heaviest edge, which is 90, right? So X has to be less than or equal to 90, isn't it? X has to be less than or equal to 90. So can X be 120? Then answer is false, right? But anyway, let's just see more. So has to be less than or equal to 90. And what about this 80? Do we have to have this less than or equal to 80 also? Is this forming a cycle with X? If you have 80, is this forming a cycle with X? I don't think this is forming a cycle with X. So 80 won't help you. So X is less than or equal to 90, right? I mean, this 100 is okay, but this 100 is even a bigger number than 90. So you can say that X is less than or equal to 90, right? This is what you can definitely say. What about bi and what about Z? Let's just find out bi and Z also. What about bi and Z? See, let's just see this bi. Okay, let's just see this bi. If this is the bi, then what you need to do? You need to keep on bringing. 120 won't help here. Let's just see 100. If 100 can help, 100 is not forming a cycle with bi, right? Okay, 100 won't help here. What about 80 and 90? 80 I think will form or not. Sorry, this is 60 also. 60 is there also. So yeah, 60 is forming a cycle, right? So 60 is forming a cycle. So you will say bi is less than or equal to 60 only. Bi is less than or equal to 60. 60 is also forming a cycle, right? So bi is less than or equal to 60. What about Z? You can say Z is less than or equal to 120 because it is forming a cycle with 120. Okay. Okay. So the next question they are asking that the value of bi, can it be 55? See, yeah, this can be 55, right? This is true. This is true. What is the largest possible value of Z? Assuming that Z is some integer and all edge weights are unique. See, Z is less than or equal to 120. But they are saying that largest possible value, assuming that it is some integer first of all, and all edge weights are unique. Now can you tell me the largest value of Z? Largest value of Z will be 119, right? In that case, if all edge weights are unique, okay. If it is given that this is unique, then this is 119. So see here, this was false. Why? Because the maximum value of X could be, we have found out to be 90. Okay, so X is less than or equal to 90. Y is less than or equal to 60, right? So this is true. This 55 is true. 120, X can be 120. This is false. And largest possible value, right? So the largest possible value, as it is written here. So what is the largest possible value? It is 119, right? It is 119 only. Let me know if you have understood this, right? Nice question, isn't it? So now I hope that you are familiar with these two cases, and we can switch to the gate cases now. I mean gate problems now. Okay, are you familiar with these two cases now? We will solve more questions regarding this, but for now let me know if you are familiar with these two cases. Should we directly jump to more cases? More questions, or should we directly jump to the PYQs? Let me know. There are many questions that I have of this kind. Okay, so for now, maybe we can directly jump to PYQs. What do you think? And then we can come back. Okay, so let's just solve few PYQs, right? Let me go to the PYQs directly. See, this pattern is very, very common in GATE also, right? So let's just see this PYQ, which has been asked in GATE 2015. So what they're saying, the graph below has 8 edges. Okay. So I think I've drawn the graph on the next page also. But anyway, so it has 8 edges with the distinct integer weights. These are the integer weights. And these are distinct. The minimum spanning tree is the weight is 36. Okay. So they have given that MST weight is 36. Contains the edges AC, BC. So AC is there, BC is there, BE is there, B is there, EF is there, DF is there, right? Okay, so all are the non-MST is given that, okay, these are the MST edges. The edge weights of only edges which are in MST are given in the figure below. The minimum possible sum of the weights, okay, of all edges, all 8 weights. So they are saying that what are the sum of all, minimum possible sum of all 8 edges. So these are the MST edges which are given. I mean the weight of the MST edges are given to you. And now they are saying that all edge weights are unique and the MST is looking like this. Okay, MST is looking like this and all edge weights are unique. Now you need to tell me what is the minimum possible weight of this AB. See, if you bring this AB, this is forming a cycle, right? With 9. So what is the I mean it could be 100, it could be 500, but what could be the minimum? So you will say AB must be greater than or equal to 9. But since it is unique, so what you can say? Since it is unique, what you can say? It must be strictly greater than 9, right? It must be strictly greater than 9. So AB must be greater than 9. AB must be greater than 9. Isn't it? Let me know. Let me know if you have understood this. So, and since it is integer also, that's why AB is 10. What about CD? CD is forming a cycle, right? CD is forming a cycle with this, which is with 15, right? So that's why it must be greater than 15. CD must be greater than 15, which means CD is 16. What about this? Is this forming a cycle with 15? Should you get confused by bringing 2 edges at once? Should you get confused by bringing 2 edges at once and then say, okay, it is forming a cycle with 15? No, just bring one edge. See, just bring, this is how we need to solve this question. Okay, all the questions we need to solve by bringing only one edge. So just bring this edge and see that this edge is forming a cycle with this, right? Which is the highest one. So ED must be greater than 6, which is ED must be 7. Okay. So 36 was the earlier weight. I mean, they have given 36, then 10 plus 16 plus 7. Okay. Whatever is the answer. See, greater than 9, which is 10, right? This is 16, this is 7. Okay. So 36 plus 10 plus 16 plus, this is 7 plus 7. Okay. Which is 69 is the correct answer here. Let me know if you have understood this. So this question has been asked in GATE, and this is very nice and easy question, right? So they will ask you, see, in the GATE it has become very common now. They will ask you for the missing edges. Okay. So in the GATE there has been questions there, they ask you about the missing edge weights. Let me know if you have understood about this particular question, right? About this missing edge weight. Is this clear? Now let's just solve one more question which is from TIFR. Okay, let's just solve one more question of the similar type which is from TIFR. Let's solve this question. This question has been asked in TIFR. By the way, those who don't know, this TIFR is even far tougher than GATE. Okay, this is very tough exam, and I mean compared to GATE, this is very, very tough. Okay, so anyway, let's just solve this question. What they are saying: consider the following undirected graph with the some edge cost missing. So there are some missing edge costs. This is missing, this is missing, this is missing, this is missing. Okay, there are some missing edge costs they have given. Suppose the wavy edges, I mean these wavy edges, form a minimum cost spanning tree for G. Then which of the following need not hold? Okay. So the MST is given to you. They are saying that this is basically the wavy edges is forming the MST. Which means if I actually draw the MST, okay, then the MST will look like this. See here, You just remove all the question mark edges. At least the MST will look like this. Okay. Is this visible to everyone that what are the numbers here? This is -2. This is -2. This is 5. This is 3. This is 3. Okay. This is 4. Okay. Maybe it is visible, right? Or if you want, I can write it in more better way. This is 5. This is 2. This is 3. This is -2 actually. This is -2. This is 3. This is 4. This is -2. This is 3. Okay. Now tell me the edge weights here. What is the edge weight of this AB? Can you tell me this AB? AB is forming a cycle with whom? This AB seems to form a cycle with whom? Okay, it doesn't form a cycle, it seems, right? See, this AB, if you connect this AB, it has to form a cycle, right? Because already you have tree, then I think this is a cycle. Yeah, this is a cycle. Because this is a tree, so it must be having a, adding one edge must be forming a cycle. So you can say this AB, let me just see if this is unique or not. Okay, they have not given anything about the unique, right? Okay. So what you can say about this AB? This AB is forming a cycle with this edge, right? I mean, this is like this, right? So with these edges. So AB must be greater than equal to 5, right? Must be greater than equal to 5. It cannot be lesser than 5 for sure. So AB must be greater than equal to 5. That's what we need to make sure. I mean, it is definitely true. What about other edges? So what about this edge? Maybe this BC. BC must be greater than equal to 4, right? What about this BE? BE forming a cycle here. So BE again must be greater than equal to 5. This BE again must be greater than equal to 5. What about this AD? AD must be greater than equal to again 5. Right? AD must be greater than equal to 5. What about this AB? AB, okay, AB we have written. So this 1, 2, 3, 4, 5. 1, 2, 3, 4. I think one of the edge we have not written. EF, right? So what about this EF? EF, you can say it is basically greater than equal to 5 only, right? This is greater than equal to 5. Okay, so let me just explain this again. See what I'm saying, that whenever you bring any, what is the step 1? Step 1 is draw the MST, right? Draw MST, which we have drawn, right? This is the MST that is given to us. Now step 2 is just keep on bringing one by one. You bring this once, see it is forming a cycle with whom? See, this is the spanning tree. Since this is a tree, bringing one edge will definitely form a cycle. So if you bring one edge, it will form a cycle with whom? It will definitely form a cycle. And what is the maximum edge it is forming a cycle? It is forming a cycle with 5. So it must be greater than equal to 5. It cannot be lesser than 5. See, this AB cannot be lesser than 5, right? Because if it is lesser than 5, then this 5 cannot be the part of MST, because this is the heaviest edge. So that's why AB must be greater than equal to 5. So that's why that is what I'm writing here. Let me know if you guys are getting or not. Okay, because this is very interesting, very nice type of question that we are solving here. Let me know if you guys are getting. This AB must be greater than equal to 5. Understood? Similarly, you talk about any edge. For example, this BC. This BC is forming a cycle with this, right? Since there will be exactly one cycle, by the way. Bringing one edge in a tree will form exactly one cycle. So this BC is forming exactly one cycle, and that is why you will say that it is forming a cycle with 4. The highest edge 4. So BC must be greater than equal to 4. That much easily you can solve this question. Now let's just see the options. Okay, let's just see the options. So this is what we have concluded, but let's just see the options. So the options are saying something like this. Let's just see the option or E. Okay, let's just see from the last. BC cost should be greater than or equal to 4. Yes, that is true. AD cost must be greater than or equal to 4. AD, where is AD? It is greater than or equal to 5. That's interesting. They are saying which of the following need not hold. See. No, the cycle is cycle. This is not a cross type cycle or something. See, let me just tell you. Okay, maybe you are getting confused that what is how it is forming a cycle, right? This is a cycle. It's not about the cross type cycle or any other type of cycle is not there. This is just a cycle. See, just a way of drawing. Okay. See, A is connected to B. B is connected to, you can draw like this. This A is connected to B. B is connected to D. You can just put this D here and E here. Okay. B is connected to D and D is connected to E and E is connected to A. This is a cycle, right? This is a cycle. It's not like that. I mean, you just twist it. Okay, it's not like that. This is a cross type cycle or something. This is just a normal cycle, and cycle is just always a cycle. There is nothing like cross type or something. It is just that this D, I can flip it here. Okay, I'm writing it here. If you write it here, then you will be able to see it simply. Okay. So bringing one edge will form exactly one cycle. Exactly one cycle. You just need to see that with whom it is forming the cycle. With whom it is forming the cycle. Okay. What is the heaviest edge it is forming the cycle? And this is the best way to solve these kind of questions. See, I can tell you one thing, that this kind of question, you do whatever, it will be very, very confusing if you don't follow this method. If you follow any other random, any other bad method or any other random method, you will not be able to solve these kind of questions. Do you remember how quickly we were able to solve that gate question? How quickly, right? So that is, I mean, if you apply that method, then you will be able to solve these kind of questions very, very quickly, right? So now we have come to the conclusion that these are our edge weights. Now, interestingly, they are saying AD must be greater than or equal to 4. We have found out AD must be greater than or equal to 5. See, are they wrong? Are they wrong? If someone says, see, I am saying my value is 10, and someone is saying that your value is greater than 4. Are they wrong? Are they wrong? Is this wrong option? Which means if I am saying it is greater than or equal to 5, isn't it automatically mean it is also greater than or equal to 4? See, this is where many students got confused. AD is greater than or equal to 5. That's what we have concluded, right? And they are saying, okay, let me just copy that. They are saying that AD is greater than or equal to 4. See, if this AD is greater than or equal to 4, can I say this is a wrong option? This is a wrong option? No. See, even if they say, see, if AD is greater than or equal to 5, then doesn't it mean that AD is definitely greater than or equal to 3? Doesn't it mean it is greater than or equal to 1, greater than or equal to 0, greater than or equal to minus 100 or anything lesser than this? See, if I am saying that AD is greater than or equal to 5 means what are the possible values? According to me, 5, 6, 7, 8 are the possible values, right? 9, 10 and so on, right? Can't I say it is greater than or equal to 4? I can say, right? But reverse is not true. Suppose I say AD is greater than or equal to 4. Okay. Suppose this is what I say. And then someone says, no, it is not greater than or equal to 4. It is actually greater than or equal to 5. Is this true? This is false. Why? Because my values could be 4, 5, 6 and so on, right? And here the 4 is not possible. So if I am saying greater than or equal to 4 and then someone is saying greater than or equal to 5, then they are wrong. But if I am saying it is greater than or equal to 5 and then someone is saying it is greater than or equal to 4, then it is okay. Then it is okay. Even they say greater than or equal to 0, then it is also it is okay, right? Even if they say greater than or equal to minus 1, then also it is okay, right? Then also it is. It is just that I have a tighter bound here, that it is at least 5. They are saying, okay, this will be starting from 4. Are you getting? So basically this D option is correct. Okay. Some students get confused that, okay, this is, we have got 5 there, they are saying 4. They are saying that which of the following need not hold? Which of the following need not hold? Will this not hold? This will hold, right? Because greater than or equal to 5 will hold, then why not this? This is holding. Okay. And then let's just see other options here. Okay. So let's just see other options here. Let me know if you are enjoying this lecture. Let me know. See, this particular method I have compiled from Stack Overflow and many other universities, and then finally compiled this method, and I'm just presenting to you. So let me know if you are understanding this. Okay, let's just say EF. The EF is greater than or equal to 5, greater than or equal to 5 here also, right? So that's fine. So I think EF is okay. This is okay. B is greater than or equal to 5. Yeah, here also. So that's fine. Yeah, now it is interesting. We have got greater than or equal to 5. They are saying greater than or equal to 6. Is this correct? See, we have got here, so these are correct. We have got AB, right? AB is greater than or equal to 5. They are saying this is greater than or equal to 6. Does this mean it will always hold? If I am saying greater than or equal to 5, does this mean that I am also saying greater than or equal to 6? No, right? No. So that is not true. Because here I am having 5, 6 maybe, 7 maybe, but here I am starting from 6, right? So it need not hold. So that's why A is wrong. Okay. Only A is wrong. This is false. Okay. So I hope you understood that how to solve these kind of questions, right? So basically, see here, there will be two cases only, right? And this case, see, let me just tell you, there will be two cases. Okay. So if the unknown weight is a MST part, then how to solve? I hope you know that you will keep on bringing the non-MST edges, right? So for example, see here, if the unknown weight, okay, here the unknown weight is a part of MST, you will keep on bringing the non-MST edges. If it is already unknown weight is non-MST, then you bring it once only. Okay, we will bring the non-MST only. So if unknown weight itself is a non-MST, then it will just one time bringing. But if unknown weight is a part of MST, then we will keep on bringing and we will see. Right? So let's solve more questions and see if you are able to answer these questions. So this question, let's just solve next question. The next question I have taken from Stack Exchange. Okay. The next question is from Stack Exchange. Let's just see if you are able to solve this question. So what they're saying, suppose that minimum spanning tree of the following edge weight graph contains the edges with X and Z. Then what are the maximum possible value of X and Z? So they are saying that minimum spanning tree already contains X and Z. So I think I have made it. Okay. So the minimum spanning tree, they are saying following graph contains the weights. Suppose the minimum spanning tree of the following edge weights contains the edges with the weight X and Z. So the minimum spanning tree already contains X and Z. Okay. So this X and Z, this and this is the minimum spanning tree that we have. Okay. Now they are asking what is the maximum possible value, okay, or of X and Z. That's what they're asking. Right? So let's just try to solve this. So this is the minimum spanning tree. Let me also draw the graph. Let me also have the graph here. Okay, the complete graph. Okay. Okay. So actually, yeah, in the question, I think this is not very clear. These are the bold edges or something. The diagram is not very clear, but don't worry about it. Okay. So I have given you the MST. This is the minimum spanning tree. You just need to tell me the values of X and Z. See, if you bring this 11, this will form. This is the only thing I think this will form the cycle with X, right? So X cannot be greater than 11, right? If X is greater than 11, it will be a problem, right? See, this, if you bring this 11, if X is, let's suppose 12, you cannot have this X. But this is already in the MST. So you will say X must be less than or equal to 11, isn't it? What about this Z? Which will form the cycle with Z? So if you bring this 12, it will not form, right? It will not form. So which will form? If you bring this 8, this will not form. I think if you bring this 14, sorry, this 8 will bring, right? So this 8 is bringing the cycle and 14 is also bringing. So among 8 and 14, you will say, see, Z must be less than or equal to 14 because 14 is causing the cycle, right? This 14 is causing the cycle. And then This 8 is also causing the cycle. Okay. So Z is must be less than or equal to 8. So 14 and 8 both are causing the cycle. 12 is not causing the cycle. This is not causing the cycle. So this is the answer. What is the answer? X must be less than or equal to 11 and Z must be less than or equal to 8. Okay. Understood? Let me know if this kind of problems are clear to everyone or not. This is the most confusing problem to many aspirants. Okay, let me tell you, many aspirants get confused. What they will do, they will bring multiple edges. Okay, they will say that, okay, let me bring 14. Okay, they will say that, okay, let me bring 14 and then 8 and then they will get confused that what to do, what not to do, right? So you just bring one edge and then once the inequality, you write the inequality, remove it and bring another edge. Okay, that's how this algorithm work. Understood? So here, this is the answer. Now let's just see the next question. The next question again I have taken from Stack Exchange. So what they are saying, in the below graph, the edge weights of only those edges which are in MST are given. Okay. So I think this was the gate problem only, right? Yeah, I think that was the gate problem only. They've also asked, someone has also asked on the Stack Exchange. So we have already solved this question, right? So, so what is the edge weight of this? This is unknown. So it must be less than or equal to 6, right? Must be greater than or equal to 6, right? Must be greater than or equal to 6. This ED. And what about the CD? CD is forming a cycle with whom? With this B, right? So CD must be greater than or equal to 15. The unique, if the unique is given, then you will just say greater if the unique is given, right? And similarly, this AB must be greater than or equal to 9. Okay. So we have already solved these kind of questions. Now, yeah, so this is the answer. Now tell me, have you understood everything very clearly, that how to solve these kind of questions? Which means questions about finding missing edge. Finding missing edge in the MST. Can we solve more questions now? Can we solve more questions? Let me know. Okay. So let's solve this question, right? Let's solve this question. And what they are saying, that suppose the MST of the following edge weighted contains the edges x, y, z. Okay. Suppose the MST contains this x, this z, and y. Then what is the maximum value of x, y, z? Okay. Yeah. So let's just solve this question. See, they are saying that the XYZ is already part of the MST. Okay, it is given to you that XYZ is already part of MST. Then what you will do to solve this question? See, if XYZ is already part of MST, then let's just see that what are the other edges will be there in the MST, right? So how many vertices are there? Can you count the vertices? 2, 1, 2, 3, 4, 5, right? 10 vertices are there. So 9 edges must be there. 3 are given to you. So 6 are not given basically, right? 6 are not given. 1, 2, 3, 4, 5 and 6. Okay. You just tell me what are these 6 edges? What is the minimum here? 10. Is 10 forming a cycle with XYZ anything? No. So I think 10 will be there, which is IJ, right? Which is 10. What is the next minimum? The next minimum is 20. It is also not forming a cycle, right? I mean, this 10 I have taken. The next minimum is 20. It is also, I think, not forming a cycle with anyone. So the next minimum is 20, which is CD, and it is not forming a cycle. The next minimum here will be 30, right? Is 30. So IH, it is 30. It is also not bringing a cycle. The next minimum here is 40, which is HG, right? The next minimum is 50. Is this bringing a cycle? Okay, I don't think till now it is bringing the cycle, right? So the next minimum is EJ, which is 50. Okay, what is the next minimum? Next minimum is 60, but it is forming a cycle, so I will not take it. 70 is forming a cycle. 80, is this 80 forming a cycle? See, let me just draw the MST till now. This is done, this is done, this is done, this everything is connected, right? This is connected. Okay, so this everything is connected, right? Now 80, 90, these will form a cycle. So maybe from this 10, I think the next I need to take 100. Okay, the next thing will be 100 because this is the cut and 100 will definitely be there. So you can say 100, right? Which is AG. Let me know if that is okay to everyone till now. Okay, that if we keep on taking the minimum and we need to check whether it is forming a cycle or not. So it is not forming a cycle with any of the existing one. So that is why you can say that this is the basically MST that you have here, right? This is the MST that you have here. Now what is the question? Let's just see the question. What is the value of XYZ, maximum value of XYZ? This is the question, right? Okay. Now you tell me if this is 40, let me just highlight it a little bit. Now you tell me what is the maximum value of X, what is the maximum value of Y, and what is the maximum value of Z. See, for X, we will bring some non-MST edges, right? We will bring this edge. So the maximum value of X will be, can anyone tell me? Just let me know that what you are getting, the maximum value of X. See, this is very interesting and very nice problem also. It will be lesser than equal to, X will be lesser than equal to 110, right? Because this is forming a cycle. What about Y? Y is basically lesser than equal to, this is forming a cycle. This is also forming a cycle with Y, right? 60 is also forming a cycle. I think many other edges. 90 is also forming a cycle. 120 is also forming a cycle with Y. 80 is also forming a cycle. 140 is also forming a cycle. So I think 80 forming a cycle, right? 60 is also forming a cycle. So I think Y is less than equal to 60, right? Let me know if these things are understood. What about Z? This 140 is forming a cycle. 80 is also, I mean, anything from here will form a cycle, right? So 80 forming a cycle, 140 is forming a cycle, and yeah, this 130 is forming a cycle. So I think 80 is the best one. I mean, the closest one, right? So 80. So these are the possible values here. Okay. So let's just see the answer. Yeah, 110, 60 and 80. See, 110, 60 and 80. Understood this? See, they are saying, in this question, they are saying this XYZ is a part of MST, right? And they have not given anything else. Interesting. They have not even given the whole MST. See, if you notice in earlier questions, in earlier questions, they were at least, they have gave at least the MST, right? They have gave the MST at least. But in this question, which I have asked in the test series, in this question, I have not even mentioned that what are the other, what is the MST. So first we need to find out the MST and then we can solve this question. Let me know if you have understood. By the way, this question is a standard university question. If I remember correctly, either this is from Princeton University, okay, or this is from either Princeton or Washington University. So this is, I mean, all the questions, by the way, from standard university, if they are in the test series. Okay, so all the test series questions are from the standard universities only. Okay, let me know if you have correctly understood this particular question. Everything about this particular question should be understood to everyone. Understood, right? Great. So now let's just move to the next question. This question is very, very high, is having very, very high upvote. Let's just see this question and let's see if we can solve this question. Okay, now let's just see. So, I mean, if the test series question is having 17 upvotes, it is actually quite good. Okay, very, very good. What they are saying in the following diagram, show that the set of the edges in the thick black lines selected are the some intermediate step of the MST algorithm. So they are saying that here, whatever we have given is this thick edges are part of MST. That's fine. But this is basically, they are saying this is not the all MST edges, right? This is some MST edges. Basically, I think they have missed one of the MST edge, okay? almost all they have given just one, just to connect this D. They have not given that, okay, who is connecting D. They have not given this. That's fine. That's fine. Okay, I have written this on the next page. So basically these are the MST edges that we have, right? Lighter edges are not yet in MST. Okay, maybe at some point in time this lighter edge, any light edge, okay, maybe in the MST, but not yet. So this is the intermediate step of the MST algorithm. Assume that we have got intermediate state using the Kruskal algorithm. Suppose that this intermediate state is using the Kruskal algorithm. What is the maximum possible value of x, y, and z? So let's just see. Okay. So they are saying this is an intermediate step. Intermediate step of Kruskal's. Then you need to tell the values of x, y, z. Okay, the values of x, y, z you need to tell. Let me know. Okay, just try solving this question and let me know what you are getting. See, one thing is for sure, the remaining edge that we want to have is either one of this, right? Either one of this. Is this okay to everyone? The remaining edge is either one of this. So basically, for now, okay, for a moment, I can say let's not worry about. Okay, I mean whether it is Z, maybe it is 120, maybe it is 110. Remaining edge is either one of this, right? But let's not worry about it. Can you at least, let's suppose whatever is the result, okay, maybe it is 120, maybe it is 110, maybe it is Z, whatever is the result, okay, can you at least tell me the values of x and y, the range of x and y? See, you will bring the non-MST edge here to calculate the value of x and y. And if the non-MST edge is basically forming a cycle with x or y, then only you will calculate the value, I mean based on that. So either you bring this Z or maybe this, it will not form a cycle with x, neither with y, right? It will not form a cycle with x or y or something. Is this okay to everyone? So basically, even though I don't know what is going to happen here in the future, still can I tell the values of x and y, the range of x and y? Most probably yes, right? See, is this forming a cycle with x or y or something? No, right? Is this forming a cycle? Yes, this is forming a cycle with x. Okay. So since this is forming a cycle with x, so you can say x must be less than or equal to 140. What about this? Is this forming a cycle with x? No. Is this forming a cycle with x? Yes. So x must be less than or equal to 130 also. Right? So x must be less than or equal to 140. It must be less than or equal to 130 also. Even though you bring these, this will not matter. Okay. Anyway, so must be less than or equal to 130, must be less than or equal to 140. So eventually you can say it is x is less than or equal to 130, right? So here x is less than or equal to 130. Now let's see what about this by. Okay, what about this by? Now you will bring the edges. You will bring this edge. This is forming a cycle with y, right? And I think this is the lightest edge. So y is less than or equal to 80 for sure. Okay. So y is less than or equal to 80 and x is less than or equal to 130. Let me know if that is fine to everyone. Okay. Now one thing is for sure, since it is an intermediate step, it is a Kruskal's algorithm, and since I have chosen x, right? Since I have chosen x and I have not chosen, for example, I have not chosen this 80. Okay, or maybe at least see none of this is forming a cycle. I have not chosen this 110 at least. So it must be also less than or equal to 110. Why? Because in Kruskal's, if I have not chosen this and I have chosen x, okay, at some point in time, if I had a choice, since 110 is also not forming a cycle, x is also not forming a cycle, I have chosen x, right? I have not chosen 110. So that is why I can say that it must be also less than or equal to 110, right? And similarly, it must be also less than or equal to z. Anyway, don't worry about it. First you tell me that is this understood that x is less than or equal to 130 and also less than or equal to 110, right? So I can say x is less than or equal to 110 also, right? Okay. Why? Because we have chosen x. This is Kruskal's, right? We have chosen x. Now what about this z? See, this z has not been chosen in Kruskal's yet, which means z must be greater than or equal to whatever has been chosen. So must be greater than or equal to this 90, must be greater than or equal to 60, must be greater than or equal to x, must be greater than or equal to y, must be greater than or equal to 70. So z must be, because z has not been chosen, so z must be greater than or equal to, you can say 60, 70, 90, 50, x, y, right? And which means the 60, 70, 90, 50 is nothing but, so let me just tell you from the z perspective that what is happening. So z is basically greater than or equal to, because z has not been chosen yet, right? Since z has not been chosen yet, so z must be greater than or equal to, max of 90 x y, isn't it? Why? Because this 90 x by 60, 50, 70, all of this has been chosen before z, and z is also not forming a cycle. It's not like that z is forming a cycle. It must be that z is the greatest, I mean some greater value, right? Some greater value than all of this. Let me know if this inequality is clear to everyone or not, that z is a greater value than all of this. Let me know. So z must be greater than or equal to 90 and xy, right? Okay. Okay. So I think you have understood this z. If there is any confusion, you can just let me know. Okay. Okay. So basically, I can say this. And similarly, I can say for x and y, what I can say? That x and y, for what I can say for x and y, they must be lesser than or equal to 110 at least, both of them. See, because this x has been chosen before this 110, right? Or maybe before this 120. So they must be less than or equal to 110, right? So this is what I have got. This is what I have got using Kruskal's. Using Kruskal's, we can say this, right? Because they are applying the Kruskal's. Now you tell me, using the cycle also, can you say? See, by must be also less than or equal to 80, right? So not just 110, but also less than or equal to 80. Similarly, x must be less than or equal to, for example, x must be less than or equal to 130, right? But that's fine because 110 is already there. So finally, what do I have is this. Finally, what do I have is something like this. This is actually very tough or little tricky question. So finally, I have these inequalities. See, I have got this using Kruskal's. I have got this using Kruskal's also. I have got less than or equal to 110 using Kruskal's, but using the cycle also. Okay, using our cycle thing also, we have got a better inequality. So I have written the better inequality here. Okay. And here for the x less than or equal to 130 we have got using cycle. Okay, using cycle we are getting less than or equal to 130, but it is not a better inequality than what we have got using Kruskal's. So that's why I'm not writing it. So the final values are this. Okay, so x maximum can take this, by maximum can take this. So z can take maximum of all of this. So it means see, the x can take 110. So what is the maximum value of x? It is 110. So z is greater than or equal to 110, right? Because the maximum of this can go even 110. So z is greater than or equal to 110, and we have got this, right? So finally you can say these are the inequalities that we have got. Okay, so z is greater than or equal to 110, x is less than or equal to 110, and so on. So they are asking that what is the maximum value. So x is greater than or equal to 110 we have got, sorry, less than or equal to 110, y less than or equal to 80 we have got, z is greater than or equal to 110 we have got, right? So what is the maximum value of x? So x plus y minus z, which means maximum of x and y and minimum of z, because it is minus, and I want to find out the maximum value of the whole. Okay, so here 110 maximum of x, 80 minus the z is 110. So this is the minimum value of z. So finally C is the correct answer here. Okay, so C is the correct answer here. This is a very, very interesting, very tough question also. That's why it has got 17 upvotes, even though it is a test series question. Okay. See, in the GATE PYQs, there are generally, I mean, 20,000 or these kind of widgets on the page, okay, on the question page, and then they got 50-60 upvotes, right? Then they got 50-60 upvotes, okay. And in our test series, like there are thousands of students, but not everyone visit every question, right? So there are generally 500 widgets only, okay, in many of the questions. So getting 17 upvotes on the test series question itself means that it is a very nice question. So we have solved many questions here regarding the particular concept that we have discussed, right? Let me know if everything is fine. Okay, let me know if everything is fine. See here the answer that we are getting is 80 only. See, 80 is the correct answer, right? Okay. Yeah. So let me know if you have understood everything in this particular session. So majorly we have solved one typical kind of questions, right? One typical kind of questions, which is basically saying that how to solve when the edge weights are missing. This was my major actually plan for this session, that missing edge weights, okay, calculation of missing edge weights of MST, because that's where many of the students get confused. And I have compiled many resources, okay. See, I have compiled from Stack Overflow, from Stack Exchange, and I have taken questions from different universities to make sure that you understand everything very clearly. See here, see, this question is from Berkeley, right? And earlier question was from Cornell University. This particular screenshot is, these screenshots are from the Stack Overflow. Okay, the Stack Overflow or Stack Exchange. So these screenshots are from that, to confirm that, okay, like whatever I'm teaching is basically written by some already verified person. Okay. Okay. So I hope you understood everything now. So if you have understood everything, then we can solve even more questions, right? We can solve even more questions. Let's just try solving some more questions, right? Let's just solve more questions, and let's see if you can answer these questions. Okay. Maybe we can solve this question. So what they're saying, this is again a question from some standard university. What they're saying, that consider the following weighted graph. Suppose we add a new edge HC. Okay. So HC is some new edge that we want to add. What are the values of HC? That for what value HC does this new edge belong to the minimum spanning tree? So if we add this, then what is the value of SC such that the minimum spanning tree has this? Can you tell me? If you have 125, okay, if you have 125 here, see 135 is definitely wrong, right? 135 is definitely wrong, because otherwise it will be the highest edge weight in this particular cycle. So that's why, okay, let's assume that this is a MSQ question. So 135 is definitely wrong. Okay, this is wrong. What about 125? What about 100? What about 90? Just let me know. What about these things? 100, 90, these things. Can you add 125? If you can quickly check, if you have 125 here, then is this a part of MST? So maybe you can check 70, 110, I think this is a part of MST, right? So 125 is not a problem. If 125 is not a problem, then I don't think 100 will be the problem, right? Or even the 90 will be the problem. So that's why A, B, D are the answers. Okay. Easy question only. Yeah, A, B, D are the answers. Okay. So there are many such questions. If you want, you can solve some of them as an homework. Let me just move to the next question. Okay, these are some good questions. Maybe let's just solve some of the questions. Let's just solve this question. Consider the following graph. This is assume that this is MSQ. Okay. Consider the following graph with the integer edge weights, some of which are unknown, indicated by X, Y, and Z. The minimum spanning tree is also drawn using the bold lines. So these are the minimum spanning tree. Okay, and some of them are unknown. So the X, Y, Z they have given are the unknown weights. which of the following bounds are satisfied by x, y, or z? Okay. So basically, you need to find the values of x, y, or z. Okay. So the MST is given to you, right? Now you need to tell me that if you bring this x, this is forming a cycle with which red edges? Okay, it will definitely form exactly one cycle, right? So I think this is forming a cycle with this, right? So you can say x must be greater than or equal to 9, right? Must be greater than or equal to. It cannot be lesser than 9, otherwise it will be a problematic situation. What about this by? Okay, by is a part of MST, right? So they are saying that the bold edges are the part of MST, right? Okay. So by is a part of MST. So for if this is a part of MST, then let's just keep it on hold. If this is not a part of MST, then we can do it quickly, right? If we bring this, then it is forming a cycle with whom? It is forming a cycle like this, right? If you bring this Z, then Z is forming a cycle with this. There will be exactly one cycle. So it is forming a cycle like this. So what is the maximum edge here? I think 12. So Z must be greater than or equal to 12. Right? Z must be greater than or equal to 12. Okay. Why? What is the reason? Because it is a forming cycle like this. Now, what about this X? For this X, if this is a okay, X is done. What about this by? For this by, if this is a MST edge, then what you will do? You will keep on bringing the non-MST edges, right? So see here that 8 is forming a cycle. If you just bring 8, if this is forming a cycle, it will just form exactly one cycle, and it is forming a cycle like this, not with y. 6, it will form exactly one cycle. It is forming a cycle with y. So it means by must be greater than or equal to 6 or less than or equal to 6. Tell me, it is a part of MST. So it is a greater than or equal to 6 or less than or equal to 6. See, if it is a part of MST, it will be less than or equal to 6, right? By must be less than or equal to 6. Okay, because it cannot be greater than 6. Okay, 8 is done, 6 is done, now 15. Is this forming a cycle with y? Yeah. So less than or equal to 15 also, but that's not much useful. You can check some value which is lesser than 6. So okay. So I think this is done, right? So y is lesser than or equal to 6. So these are the answers which we are getting. Greater than or equal to 9, lesser than or equal to 6, greater than or equal to 12. Greater than or equal to 9, lesser than or equal to 6, greater than or equal to 12. Okay, so I think A, B, C are the answers. Z is greater than equal to by. Yeah, it is always lesser than 6. It is always lesser than 6. It is always greater than equal to 12. So yeah, that is correct, right? That is correct. Is this understood? Let me know. So I hope this is understood, right? I hope this is understood. That Z is greater than equal to 12. So here since this Z is also greater than equal to 12 and by is always less than equal to 6, so that's why D is also correct, right? Because it is greater than 12, it is less than equal to 6. So A, B, C, D are the correct answers for this MSQ question. Yeah, A, B, C, D are the correct answers, right? So this was also a nice question, isn't it? Now let's solve this question. Let's solve this question and let's see if we are able to solve this question, right? So what they're saying, assume we have two graphs G1 and G2. Also assume that we have T1 which is the MST of G1, T2 which is the MST of G2. Okay. So let's suppose this is T1, this is T2. Now consider a new graph G such that it is a union of both the graphs E1, E2, E3, where E3 is a new set of vertices, edges, okay, across this cut. So they are saying this is G1. G1 is having some MST. G2 is also having some MST. What we need to do, we can do one thing. We can take a union such that we can connect both of them, okay, using some edges. Following is an example of G might look like the dash edges are E3, the solid edges in G1 on the left are T1 and T2, okay. I hope you understood. So they are saying this is T1, this is T2, and these are E1, these are E2, and E3 is this, okay. E3 is this. I mean the edges here, okay, the edges here are basically the complete graph, okay. I mean the multiple edges might be there. So this is E1, this is E2. Now assume we want to find the MST of this complete graph G, okay, using this algorithm. There is some algorithm that they have proposed. Let's just see that algorithm. Okay. So what they're saying is that maybe MST. I mean, this is the name of the algorithm. Now what they're saying, E minimum equal to a minimum edge weight of T1, T2, E3. So basically they are giving this T1 as an input, T2 as an input, this E3 as an input. Okay. Now they are saying a minimum edge weight in E3. So you find out the minimum edge weight in E3 and then you return it. So they are saying that you have some MST here already. You have MST here already. Whatever is the minimum edge weight, okay, you just take it and then you say this is the MST. Now, which of the following is true about this algorithm? Algorithm correctly find the MST? Okay, let's just see if algorithm can correctly find the MST. What do you think? They are saying there is some MST here. Okay, maybe there is some MST here. There is some MST here, right? Now, let's suppose this is 10, 20, 30. Okay, this is the MST. Now it is also some edge weights. Okay. Now let's suppose they are saying that you have some E3. You connect this. You find out the minimum. Whoever is the minimum connecting, right? Whoever is the minimum connecting across this. Whoever is the minimum connecting. Let's suppose this is 50, this is 100, this is 150. So minimum is 50 here, right? Minimum is 50 here or something like this. So what I mean to say is this. Let's suppose this is, okay, this is 50. Yeah, this is 100, this is 150. Then they are saying you keep this MST, you just have this 50. And this is the final MST that you will be getting of this whole graph. Will this always be true? Tell me. Are you getting the question? So you keep these two MSTs and then you tell me, will this always be true if you can connect like this? See, the minimum will be there, but they are saying you will be just having one minimum. Okay, that's the thing. The minimum will be there, that's fine. But that might be the case. See here. See, you are having this 10, 20, 30 or something, right? Okay. Here also maybe something, maybe 10, 20, 30. Now, I mean, this is a cut, so minimum you will definitely take, but it might so happen. Okay, it might so happen. Let's suppose these are the, okay, just to simplify, I'm just taking easy example just to tell you one thing here. Let's suppose this is the MST, this is the MST. This is having, let's suppose, some weight which is 10. This is, let's suppose, having some weight which is also 10. Now, this edge, there might be multiple edges in between, right? There might be multiple edges. Let's suppose these edge weights are very low. Okay, I mean, these are bringing a very, these are bringing a very good value to us. These are very low. Still, you are saying that you will just take one of them. Tell me, if you are having something like this, if you are having this 10, and you have multiple options to connect these two, these four vertices. Okay, will you ever use this 10? Let's suppose you have this option to connect these two, and this option to connect these three, and this option. Let's suppose these all are 1, 1, 1. Okay, which means finally it will get connected. Won't you choose this 3? The minimum spanning tree is 3. See, one of them you will definitely choose, but they are saying only one of them. Okay, you keep this as it is. You just choose one of them. Okay, no, that is false. See, this is very nice question. See the counter example. This is G1, this is G2. Now if you bring this, then the new MST is this, right? And they are saying the new MST is this. 10, 10 and 1. No, you will keep the minimum. That is a cut property. But maybe after bringing more edges, maybe these edges become useless, right? That's what we need to see. Maybe these edges become useless. So hence you will say that this will not even find the correct MST, right? Does not calculate. So that's why D is the correct answer here. This is also one of the very nice question of the test series only. Okay, this question is again from the test series. Okay, So D is the correct answer here, right? Cool. Now let's solve more questions which are gate PYQs itself. Okay. Let's solve more tricky questions where we have got many upvotes, right? Let's solve tricky questions where we have got many upvotes. Okay, let's solve this question. What they are saying? G is a weighted connected undirected graph with distinct positive edge weights. Okay, so yeah, just a second. I think the pen is not working. Yeah. Okay. So let's just see what they are saying. They are saying that this G, right? We have a graph G, which is this G is a weighted connected undirected graph with distinct positive edge weights. Okay, they are saying positive. That's good. If every edge weight is increased by some value, then which of the following is true? Okay, yeah, this is easy question. I think we have done this kind of a minimum spanning tree. This will not change. Yes, that is true. Shortest pair does not change. No, that is false, right? We have seen these kind of questions. So see, if you have the shortest pair, then shortest pair may change because it may give you the unfair advantage to some of the path. Maybe earlier, let's suppose earlier this was the, let's suppose this is 3. Earlier, let's suppose this was the minimum. But if you add, let's suppose 5 everywhere, then now this is minimum, isn't it? So shortest will change, right? So what is the answer? Answer is A, which means that shortest might change, but minimum spanning tree won't change. Okay. So let's do this question. What they're saying, let G be a complete undirected graph with 4 vertices and 6 edges, with weights being 1, 2, 3, 4, 5, 6. So they are saying there are the 4 vertices, okay, 4 vertices, and undirected graph is this, and weights are 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, this is the complete graph basically. Okay, the maximum possible weight that a minimum weight spanning tree. Okay, that's interesting question. What they're saying, that see, they have not given, see, they have only given this is 1, 2, 3, 4, 5, 6, right? But they have not given that which one is 1, which is 2, which is 3, which is 4, which is 5, which is 6, right? They have not given this, right? It is up to us. Maybe what we can do, see, they have just said that it is a complete graph with 4 vertices, right? Maybe let me draw this. Let me use different color for these 2 edges. Okay. Now, maybe this is 1. I mean, they have not given this, right? So this is very interesting to note that they have not given that which one is 1, which one is 2, which one is 3, which one is 4, which one is 5, which one is 6. So maybe you can say one of the possibility I'm just writing, right? One of the possibility. Okay. So only one of the possibility I'm writing. Maybe this is 1. Maybe this is 2, maybe this is 3, maybe this is 4, maybe this is 5, maybe this is 6. Maybe this is 1, this is 2, right? This is 1, 2, this is 3, right? Maybe like this. Okay. Yeah, and 4, 5, 6, right? So there are multiple possible ways. Now, if you find out the minimum spanning tree here, what is the minimum spanning tree? Okay, so you are able to choose 1, 2, 3, right? Because 1, 2, 3 is not forming a cycle. Okay, maybe I can have one more example to differentiate the thing. So let's suppose this is 1, this is 2, this is 3, this is 4, this is 5, this is 6. See, the minimum spanning tree here, minimum spanning tree will be having just 3 edges, by the way, right? So it will be having 1, it will be having 2, it will be having 3. So it is 1, 2, 3, right? You are able to take 1, 2, 3. Here also 1, 2, 3 is not forming a cycle. So you are able to take this 1, 2 and the 3. So 1, 2, 3 you are able to take. Here since 1, 2, 3 is forming a cycle, right? So maybe Kruskals will take 1, and then Kruskals will take 2, then 3 is forming a cycle. That is why you will go for 4, right? So the minimum spanning tree will depend, the weight of the minimum spanning tree will depend that what kind of distribution of the edges you are having, right? What kind of distribution of the edges you are having. So the question is that the distribution is up to you, the maximum possible weight that you can have. See, you can have multiple distributions, right? Here you are having the weight as 3 plus 2 plus 1, 6, here you are having 6, here you are having 7 or something like this. So they are saying what is the maximum possible weight you can have of the minimum spanning tree. See, whatever you do, 1 and 2 cannot form a cycle, right? I mean, only 2 edges, you will definitely choose 1 and 2. Okay, wherever it is. Okay, you will definitely choose 1 and 2. Now, since you want the maximum, then at max the next thing will be 3, right? The next thing will be 3. I don't want to take this 3. Why? Because I want to take more. See, the Kruskal will taking the minimum. There is no way I can avoid this 1, 2. Okay, there is no way I can avoid this 1 and 2, right? Now I want to take the next minimum. If I pick this 1 and 2 like this, 1, 2 and 3 like this, then sorry, this 1, 2 and 3 like this, then I will be basically picking 1, 2 and 3. It is a minimum spanning tree, but it is not a maximum weight minimum spanning tree, which means I want to avoid this 3, which means I want to have a distribution such that it makes a 3 makes a cycle. Okay, because I want to avoid this 3. Are you getting my point? Okay, maybe you're getting. See what I'm trying to say. This is 3, right? So here what I'm trying to say is that this is 1, 2 and 3, and what I want this 3. Okay, I want this 3 to make a cycle basically, right? I want this 3 to make a cycle. So if this is 1, this is 1, this is 2, I want this 3 to make a cycle. So I want this 1, 2, 3 like this. Okay, I want this 1, 2, 3 like this, because 1, 2 I can't avoid. At least I can avoid 3, right? And then if I can avoid 3, then the next minimum will be 4, right? So I have to take 1 and 2. The next thing that I can avoid is 3 only, right? Can I avoid 3 and 4 both? And can I directly take 5? No. Once I take 1 and 2, 3 will be making a cycle, then 4 will not be making the cycle, right? 4 will not be making the cycle. So 1, 2 and 4, right? I cannot avoid this 4. I want to avoid lower numbers, but I cannot avoid this 4. So that's why 1, 2 and 4 I have to take. So that's why 7 is the correct answer here. This is also a very good question where the answer has got 1, 4, 1 upwards. Okay, but I hope you understood this question very clearly. Okay. Now this question, if you remember the MIT question, I told that this is a GATE question also, this is a test series question also, right? Test series question also. This is the line I was talking about. If E is the heaviest weight in some cycle, then every MST must exclude, this is the line. If it is the lightest weight, then every MST must include this. No, that is wrong. Why that is the case? See, they are saying these are the distinct edge weights, okay? They are saying these are the distinct edge weights. Now, if this is the lightest, then should every MST include this? No. What is the reason? If this is 3, 4, 5, see, this question has got 1, 1, 3 upwards. Okay, just understand that. This is 3, 4, 5. It is the lightest, but it could be the heaviest of some other cycle, right? This is 1, 2. And since it is the heaviest of some other cycle, that is why, because of the cycle property, I will not take this. Okay, the lightest could be heaviest of some other cycle, right? Could be heaviest of some other cycle, right? If E is the heaviest edge of some cycle, then every MST must exclude it. Yes, that is true. So 1 is false, that is true. That is why 2 only. B is the answer here. Okay. So B is the answer. Understood? This question was also very, very nice. Yeah. So I think we wanted to solve all of these questions. Maybe you can visit some more questions, and we will bring one more marathon. I think this has been quite a long time here. Okay, so maybe we can for now we can stop, and then we can have one more session if that is required. So in this session, majorly I wanted to focus on some theorems, basically cut property, and mostly about the cycle property, right? Cycle property. This was very important to solve many questions, and we have majorly focused on finding the missing edges. Missing edges. Okay. So this was all about the MST discussion. Now you can solve any PYQ which is given to you. Okay. You can solve any question. We have solved every question, every variation which is required. Okay. So there is one small thing. Okay. Just a 5 minute of discussion I want to do here, which is about the minimum spanning tree with modification of edges. Which means sometimes they might give you. They say, suppose MST is given. Okay. They will say question will be something like this. Suppose MST is given. Now we for example increase some weight. Okay, so increase edge weight of some, for example, non-MST edge. Okay, then you calculate the new MST, some non-MST edge. Then find new MST. Okay, suppose this kind of question is given. So if some MST is given to you, and then they say that okay, there is some edge which is not a part of MST, you increase this edge weight. Will this change your MST? Will this change your MST? Then the answer is no. Okay, if you're increasing non-MST edge, then it will not change your MST. So the new MST is same as the old MST. Okay, but if you increase something here, so if you increase something here, which means MST is given to you. If you increase, let's suppose, okay, this is the MST, okay, or some other MST, you can draw something like this. If you increase some edge weight of the MST, then what you need to do? You need to check whether this is still the old MST, is still the new MST or not. So there are 4 cases, right? There are 4 cases, which is basically like this, that edge in the MST and you decrease the value of it. Edge is not in MST and you decrease the value of it. Basically, if edge is in the MST, you decrease the value, and in that case, you are decreasing the value of MST edge or non-MST edge. You increase the value of MST edge or non-MST edge. Then how to calculate the new MST? See, if this is MST, you are decreasing. So here the old is same as new. If this is non-MST and you're increasing, here also old is same as new. Old is same as new. If you are in MST or not in MST and then you're decreasing, then maybe you need to check, right? So these 2 cases we need to check. So let's just quickly see that how to check for these 2 cases, right? Which means if there is some edge, right? There is some edge that is there and which is basically not in MST, and then you're decreasing the value. For example, maybe I can draw some example here. See, for example, this is, let's suppose, the graph, and these are the MST edges, right? These are the MST edges. Now, if this edge in the MST, and let's take this case, which is, okay, let's take this 2 and 3, which is edge is not in MST and these things, right? Okay, so let's take this 2 and 3. So suppose this non-MST edge is there. Okay, this is non-MST edge. And what you do, you increase this value. If you increase the value of the non-MST edge, then how to find the new MST? Okay, let's just check. Let's just check how to find the new MST. Okay. Can you suggest me any way how to find the new MST? If the edge is not in MST, then what you will do? And if you decrease it, okay, for example, what you can do, that's very easy actually. What you can do, okay, let's suppose a non-MST edge and you decrease the value. Let's suppose you decrease this value. Then you need to check whether this particular edge is still, okay, see, this particular edge was not in MST. What was the reason? Because it was the heaviest edge. That is the only reason it is not in MST, right? That is the only reason. That is why it was not in MST. That was the heaviest edge. Okay. Now you need to check whether it is still, okay, case 2 or maybe this, whether it is still the heaviest. Okay, still the heaviest. How to check? In the cycle. In the cycle. That's all. Okay. So how to check? You need to check all the edges. You need to check the cycle, that what are the cycle it is forming. So I'm not going to much detail that how to check the cycle and all. It is using DFS in order of B plus E. Actually, you can do. You just need to check whether it is still the heaviest in the cycle. Okay, check the cycle and find out the heaviest edge, maximum or minimum. Okay, maximum edge you can find out. Similarly, if it is an MST and you are increasing the weight, okay, then you need to check if it became now the heaviest. Now it became the heaviest or not. So it is just heaviest in cycle. You just need to check whether now it has become the heaviest in cycle. If not, you keep it as it is. If it has become the heaviest, basically you reject it. You take the other like the next minimum basically. Okay, I mean you will not take the heaviest basically. So in both the cases, you just need to check the cycles. That's all. Okay. Anyway, this was just optional discussion. That is okay. Gate has not asked any question from this, but I just wanted to tell you quickly, okay, in just 5 minutes, that in these two cases, old is new. In these two cases, we need to check cycle. Okay. That's all. So that is all about our MST discussion. I hope every one of you liked this session. So please, okay, everyone, I'm just requesting everyone that if you have really loved this session, then please comment it out and just let us know that how much you have liked this session, because we are putting many efforts just for every session. Okay, compiling many resources, compiling all the gate PYQs, compiling every particular theorem, every particular lemma, and whatever the possible ways. So if you like it, just put a comment after this video so that we really get motivated. Just like you, we also need some motivation, right? So that's why just put a comment so that we really get motivated to bring such more sessions. Okay. Thank you.